plane wave. This is called Bosishto, and the other one is Arundhati. So Arundhati and Bosishto, these are the, as you know, it is in Saptarshi Mandal, binary, very visual binary actually. So we have these two telescopes are there, and this is the telescope room. The retractable roof. Automatically it gets retracted by electric, power. There are motor there, and this is the telescope, plane wave telescope. Okay. This is very user friendly. Students can handle them themselves. It is unlike many other places where telescopes are not really touched by the students or even faculties. And here people can people can actually adjust everything of the telescope, and they can learn everything how the telescope works ins and outs. Okay. Now this is the sky is extremely good. We get about 100 days per year. Very good observation. This is a picture we took with our 10-inch telescope. As you can see that even the sky is, this is the Orion Nebula, where the star forming region, and the picture is sufficiently good clarity. I will come to this. And this is another picture of a body of, let us say, meteor, our comet. You can see this comet. You can see this is also taken by our telescope. This is a CCD camera. So this is grainy. This is also a supernova. As you can see the whole. I hope you can see the entire spiral galaxy. Beautiful spirals have come. And also you can see the supernova outburst. Okay, this is an example of how the telescope worked during the lockdown time. During the lockdown, the sky was so good that you see much fainter stars, like all these stars which are circled by red color. These are the stars which are new. New means which were not seen when the lockdown was not there. For example, this was the before lockdown. Before lockdown, sky was like this, and after lockdown you have at least twice as many stars. So the sky is extremely good, and up to 13th magnitude we can even take spectra, and science can be done very properly. So this is one of the pictures of an asteroid which came very close to the earth, and then it went away. So this is a picture every day we took with our telescope. One is by by Bosishto and by Arundhati. So everything is working perfectly. And of course, when the last year, as you know, that when Saturn and Jupiter came extremely close to each other, we took this picture, and this picture also came in Anandabajar Patrika, which is very popular newspaper here, and this is also a popular newspaper article on our facility. So this is the spectroscope, spectrometer. Spectrometer is high resolution, is there, 0.1 pixel, 0.1 angstrom per pixel. It's a very good spectrometer. So and we have a couple of CCD, we have at least 4 CCD cameras, sufficiently good resolution. Okay, so taking spectroscopy and photometry and imaging is not a problem. This is a picture of the spectrum of the sun, and many of the absorption lines are the telluric lines of our Earth's atmosphere. You can see the infinite number of lines coming with using our spectrometer. This is direct. This is not even through a telescope. So direct observation of the sun through the spectrometer, and so everything is in the working condition. This is an example of the students' project. There are many students go there, and we invite a lot of students can go there, stay there. Of course, there is a cost involved with food and accommodation, a little bit more nominal, but people can stay there and spend overnight and even do projects, 7-day projects or so. This is an example of a project people done. This is Saturn, and this is Saturn's ring. You can see, and when we take the spectrum of the ring, you can see the red shift and blue shift. Blue shifted, one side of the ring is red shifted, the other side of the ring is blue shifted. So it tells you that the ring is moving, some part is moving towards us, some part is moving away from us. And if we plot the data of the velocity on this Saturn as well as on the ring, you can see that the ring is moving in a Keplerian velocity. So you can prove that the Kepler's law even by watching Saturn. This kind of projects I think students should do and could be able to do at our campus very easily. And this is an example of a very two close star, Mizar and Alcor. This and Alcor, and there is one more non-identified star inside. and not classified. So you can see all the spectra of all the three of them came together. Okay, and this is an example of the spectra taken of this our ring nebula, and you can identify some of the lines. Of course, there are lots of noise, and that noise can be reduced by integration of the beans. Here, no, these are raw data. These are raw data, but you can still identify some of the lines. So the goal is to observe some clusters. So this is a summary of the pictures. You can see that the large number of students here. Okay, and this is the control room where the students work, and the next room is the telescope room. So telescope room and the control room side by side. There are two rooms below which are observers rooms. If the observers get tired or there is some cloud, they can take some rest. So there are supernova. You can see supernova decay. After about 15 days, this supernova got decayed into almost fainted. So this is also we have been following. The light curve of the supernova was observed. You can see the light curve. And this is another supernova. Okay, supernova, this is the intensity. We can calculate and we can see the light curve, how it's decaying. So good signs can come out. Similarly, there are variable stars, lots of fields we have studied, and we can study the variability, we can study the periodicity, and these are done for using our 24-inch telescope. There are automatically one can write programs so that the sky can be scanned automatically. Every, let us say, 10 seconds of exposure, take picture, then after that it goes to this one, then after 10 seconds it goes this one, after 10 seconds it goes to this field and comes back again. So every 40 seconds it will be automatically scanning certain part of the sky. So we can do a large number of scanning of a large region with our telescope. Now these are the CCD camera pictures. Now even a GRB, a gamma ray burst, was also observed using Bosistor. Okay. So conclusions are that the telescope is the largest in Eastern India and it is useful. It's a good telescope, it's a new telescope, totally functioning, and we have tested using imaging, spectroscopy as well as variability studies. So I believe that the many new discoveries are awaiting. It is also very good for sky survey. Most interestingly, this sky telescope is fully owned by us. Nobody is going to take its time. Only our scientists can use it. Right now there are two scientists, Dr. Ashish Raj, who is in charge of this campus right now, and Dr. Devendra Beast, scientist C, and there are three junior research scientists, 3 or 4 junior research scientists. There are Mohit and the Kuldeep and Rajesh and I think Onkur or Onkon Kundu, I think. So these 4 people are there, and we invite a lot of other scientists also to join as a research fellowship, to taking research fellowship. Best thing would be that if you have your own fellowship, you can join, and we will be very happy, and they will also like the campus to grow, and the spirit of observational science grow also in eastern part of India. So far it was in other places. Okay, so I think that this is all that I have to say. If you have any question, I will be able to answer.
Thank you so much, Professor Sandeep Chakrabarty, for a nice talk. Now it's time for a few questions. You can also type your questions on chat box as well, so you can ask.
Are there any questions in the YouTube, for example?
Yeah, someone raised a hand.
Yeah, Professor you can ask your question.
Okay.
Yeah, I'm Yingui from Tsinghua.
Okay.
I wonder how far from your main campus to the telescope.
See, the telescope itself is a separate campus, and our main campus is in the Calcutta city. Okay. Main campus of Indian Center for Space Physics is located in a very posh area next to a metro station in the city of Calcutta. Okay. And from there, it takes about 3 hours to go to the campus of observatory. So observatory campus is about 80 kilometers away, and it takes about 3 hours because the road is a little bit, part of the road is through villages, and but so main building and this campus, they are separated. They are, and people can stay there totally, and time to time they can come to the main campus if they need to. Otherwise, we work through online meetings, etc. Yeah, that's a village. That's a total village, and this is Calcutta. Calcutta, you cannot see even 2 stars on the in the night sky. So it is fully lighted. So there is no point in having a telescope here. So entire facility is in a very remote village, and the sky is sufficiently good.
Thank you.
Okay. Okay, Tomal Bosak says that a very nice presentation, whom to contact if we want to visit. Please contact, please watch the our website. There is somebody named Jyotisman Moitra is there. You can also directly contact Dr. Ashish Raj. And I think in web page you can go, and best thing would be to collect 10 to 20 people, and we can certainly manage to. Right now the main building has not been 40 students can stay there at night. That guest house is not completed, but at least there are occasions where 20 people went there and people stayed there in dormitory type buildings. We have sufficient number of buildings. That is not a question. That is not a problem. But if you come as a group, it will be nice. If you come alone, then we will encourage only for doing research purpose or in doing projects or as a student. Anybody else?
If no more questions, then let's thanks the speaker again.
Okay. Thank you.
Our next speaker is Professor Wen-Ping Chen, and he obtained the PhD in astronomy from Stony Brook University in 1990 and was a French postdoc fellow at DTM, Karenji Institution of Washington from 1990 to 1992. He then joined the National Central University in Taiwan and is now chair professor with specialties in observational star formation, star clusters, substellar objects, and cosmic variability. Now I welcome to Professor W.P. Chen. You can share your screen.
Is it on?
Yeah, it's okay.
Are my slides on?
Yeah.
Yes.
Yes.
All right. So thank you very much. It's a pleasure to share with you my experience. I'm not going to talk about a single telescope. I'm going to talk about some projects that I have carried out or on the drawing board about small telescopes. To me, small telescopes are anything less than about 2 meters. And my philosophy has been that the difference in the telescope sizes is not just the integration time, it's different size. So small telescopes, medium-sized telescope, and large telescope should do different size. I'm from National Central University in Taiwan. So I give my
Hello.
There is a voice problem.
Professor Chen, you are muted actually. Hello.
So you didn't hear me?
Yes.
Now it's fine.
All right, I'm sorry. All right, Wen-Ping Chen from National Central University. In my mind, small telescope means anything less than 2 meters. And my philosophy about telescope, about the size, is not the difference is not in integration time. It's small telescope, medium-sized telescope, and big telescope should be doing completely different size. So astronomers have been pursuing sensitivity and also resolutions of different kinds. Spatial angular resolution, spectral resolution, and now it's time to do time domain, so time resolution. So in Taiwan, we are located in a special place, so we are particularly interested in time-honored events. So only us, at this longitude can observe. But at the same time, we also joined global telescope relay networks, so we could also contribute. We provide our service to bigger science. And at the same time, we also sign up. We are partner of some sky surveys, and we would try to follow up some possible alert to secure the discoveries. Of course, the requirement for a telescope is, for this kind of operation, is we require efficient operation. Either the telescope system has to respond to any requests rapidly, and the telescope has to be operated robotically or automated. So the idea is we lead some efforts. We are first author, lead author for some papers, but at the same time, we co-author many other papers, which we couldn't even find our names, but I consider these as the service to the community. I start with a slide showing this part of the world. So this is where Taiwan is. So this slide shows the telescope bigger than 2 meters. So these are medium-sized telescopes. There are a bunch of, in Hawaii, but there's Australia, New Zealand. There's 1 4-meter in Indonesia coming up, Japan, Korea, Beijing, China, Yunnan, Thailand. Certainly in India, we have the Hanley and also the Bethel 3.6 meter. So at that time, we thought we need one here. We are well located in West Pacific at low enough latitude to observe both hemispheres. Furthermore, we have many high mountains. Taiwan is geologically young. We have many peaks. So the weather is not very stable, but when the sky is clear, we could provide a very good opportunity to observe. This is Taiwan sideways. So this is the south eastern part of China. So the western part has been immigrated from China. Our observatory is right here. It's still quite dark, relatively surrounded by high mountains. So and this side is where our Lulin Observatory is. This is the only research level observatory in Taiwan hosting a 1 meter telescope. This is right now the largest. We have many 50 centimeter, 40 centimeter, and recently we have 3 more 50 centimeters. So it's populated by small telescope. It's the only observatory in the world without road access. Everything would have to be carried up, or for really heavy duty work, we rely on cable cart. All right. So here gives the observatory. It's not very high, nearly 3,000 meters. The sky is relatively dark because it's next to a national park. The seeing is okay, but as I said, it's highly variable. It could be completely clear in 1 hour, but next hour could be completely covered up. So it's variable. So it's not good for long time monitoring program, all right? But it could rely on. So here I didn't even put down the references. So we have been doing blazar variability. This is supposed to be a video clip showing an asteroid. We discover supernovae. We combine with other observatory to have more than a decade a light curve of young star, including superluminous supernovae. We study hypernovae, and this would be actually our next step. We certainly joined the fund to study exoplanet, including the TTVs. So this is astroseismology campaign. So this is a light curve. I'm sorry you cannot see the details, but Without Lulin, this was previously there's a gap, but now with Lulin, we could cover this time zone. So it's critical. Occasionally, we also provide ground support to space programs. So, or time domain opportunist observations. This particular project is very worth mentioning. At Lulin, we used to have 4 50-centimeter very wide angle telescope. The idea is illustrated in this diagram for Kuiper Belt object, which is too faint to be observed by any large telescope by reflected sunlight, can be detected by occultation. So by detecting chance of stellar occultation, each will last less than 1 second, we could conduct a census of this object. The program started in year 2000 and ends 17 years later. Now we took down these 4 wide field telescope and we moved 2 of them now to China, to Xinjiang, the westernmost point of China. So right now we're going to still use the high cadence capability up to 20 hertz sampling of thousands of hundreds of stars simultaneously. We would like to conduct transit survey of exoplanet, but on bright stars. These stars of first, second magnitude cannot be observed by any telescope, just too bright. But we provide very fast, high-speed photometry to study these stars. This is one example. This is very old. We observe a predicted occultation of a background star by an asteroid. So we see that 3 telescopes detect this occultation event simultaneously. So that allows us to confirm the reliability of this event. And certainly later we could use different filter. This is another triumph, Taiwan American Occultation Survey. This would detect 1 GRB within 1 minute after the burst. So this is really nice. We have 3 telescopes, each detect this event separately. These are all history. Once we moved the telescope to Xinjiang 2 years ago, we monitor for 1 flare star. It's an M dwarf, very nearby, for 1 week. We use a 1 meter in Xinjiang and a 0.5 meter of one of those wide field camera, 300 kilometers apart. So with different sampling function, we were able to detect flares. So other than stellar frequency, we could diagnose for the same giant flare with different sampling function, we could reconstruct the so-called true profile, all right? So you see that 1 telescope observed compared to the quiescent stellar flux, 0.8. So it's really bright. It's reached 80% of the stellar flux. Another telescope, the other telescope, measure 0.4. So 1.4, 1.8, because it's sampling the same flare at different timing. We could reconstruct the real flare actually is 1.6 times. So the timing, the rising time, decay time would be different with only single telescope. So this is the power of 2 telescopes. Exactly 1 year ago, then we started a campaign involving Southeast Asia, including Aries in India, and further west in Majdanek and Nanshan, Xinjiang, Xinlong in Beijing, Weihai in Shandong, Lulin, the easternmost site, in Yunnan. 7 sites using still a monitor for same flare star, but we managed to allow at least 2 telescopes to use the same band. So we have 2 bands, So now we have multicolor monitoring of the same flares. All right. Actually, with Lulin and Aries, we have polarimetry. So we have simultaneous, this is just the observing log of different colors with polarimetry. The data is still being analyzed, but we're very excited of this kind of campaign, or using small telescope, no bigger than 1 meter. I used the rest of my time talking about some link to major telescope. Taiwan was the only partner in Asia that joined the Pan-STARRS. So using this, we learn about time domain science. We learn about how to handle, how to storage, how to distribute data, large data, big data. So Pan-STARRS 1 is gone. Now it's Pan-STARRS 2. Two telescope system, we still have data right, even though we don't use it anymore. The data are public domain. Our university also, our group also joined the Zwicky transient facility. Instead of Hawaii, now it's carried out in Palomar Mountain using 1.2 meter wide field to do sky survey, a 1.5 meter telescope to have the SED machine to do classification of transient phenomena, and rarely then use 5 meter telescope to do spectroscopy. So on the same mountain top, one do discovery, classification, and confirmation at the same time. All right. So I will skip this. Actually, the whole Taiwan community trying to monopolize a different kind of telescope in Hawaii. The latest effort in our site is to use our 1 meter telescope at Lulin and join other similar 80 centimeter up to 1.5, maybe 2 meter size to do an exo-Earth. It's an exoplanet search program, but we focus on Earth-like objects. In other words, we search around nearby M dwarfs. The search is going on. We have been into this for 2-3 years. We have exoplanet science, but we also have flare star science at the same time. Pretty much like what people use Kepler and TESS to do stellar science, as well as exoplanets. The last 2 slides is to show the LSST. I do not need to go through this. You all know it's the next generation 8 meter telescope to patrol the skies cyclically. It affords wide field and good angular resolution, small scale at the same time, and would survey the same patch of sky every few days. It will go on for 10 years. LSST is really the next generation time domain machine. It would produce millions of alerts per night. All right. So in order to accommodate that, so our group is also a member. Well, we have data right of LSST, but in exchange, this is the last slide. Our latest effort is to build a 2 meter telescope in Mexico. Mexico is host the next generation TAOS program. I told you about the KBO occultation. The next generation is here, for which the sky condition is better. The infrastructure is already there. Our 2 meter is ready, actually already been ready for 10 years. Because of some site issue, we couldn't put it in Taiwan. We decided to put it here. It's 3-hour time zone later than LSST. So it would be able to follow up the LSST discovery on first timing. All right. And then we could also follow up on 12 hours later, and we certainly can work during the daytime where it's night. So there's no night and day for this. So let me conclude the same. At NCU, at least for me, my group have been doing time domain science with different telescope. Some of them we lead the science, some of them we join bigger project we serve, we provide our data to the group, but some of them we also take some lead of some sub-project in this big telescope. So our 2-meter telescope is the next step. It will be ready in 2024, the same time frame as SST. Thank you very much.
Thank you so much, Professor W.P. Chen, for a nice talk. Now it's time for a quick question.
Professor Chen,
Yes.
so our institute is very new and our facility is extremely new, and you are certainly one of the most stalwarts in the subject, and particularly small telescopes. We should be able to do some science. So what is your opinion that we should first try, and is there any scope for collaboration, or can we be in a network in future? Because I have shown already its capabilities, that the best set of pictures can come, the spectrometer is doing perfectly well, so location is also good. So somehow we will be encouraged if we can be put in some kind of network. In Dr. Ashish Raj is there, Dr. Beast is there, so they can be put in some networking observation.
Yeah.
So our institute can. Yeah.
Indian astronomers are experienced, right? So far as I know, in Aries, they also joined quasar kind of monitoring or astroseismology. So you are welcome. If you want me to link you up, I'll be happy to. So you can approach them to be a part. The problem with that approach is that you will be one of the 30, 50, 100 authors. So for me, it's fun. It's okay. But you should think of some science that you can lead. You can make use of the same network. You convince the whole network to do 1 or 2 campaign for you, right? So
Yeah.
yes, for our small scale campaign, for example, I show you this 7 telescope flare star. I would be happy to allow to invite you to join. I'd be happy to. So I'm glad to have this workshop. I think that's the one of the purposes of this workshop is that we get to know each other and we can collaborate.
Yeah, and one thing is, of course, in AGNs, ours is small telescopes, so I don't know in the quasars we can contribute very much because they are generally faint and far away. But
Oh, no. Our main workhorse for AGN is our 40 centimeter.
I see. So okay, but again, your point is well taken that we will be part of 36 here. Other than if we find some exciting something, then we request others to do a simultaneous observation would be very nice. But the other networking that you mentioned, that 7 or 8 telescopes that you are already there, maybe a part of our time we can do your science also. It will be nice for us because it's a learning phase for us. So we will be very happy to join a part of our time.
By all means, it will be my pleasure. I already put you in.
Yeah, okay, thank you very much.
Very good.
So if no more questions, then let's thanks the speaker again.
Yeah.
Our next speaker is Professor Ing Gyu Jiang. He has a PhD at the University of Oxford, UK in 1999. He was a postdoctoral fellow at the Institute of Astronomy and Astrophysics, Academia Sincia, Taiwan from September 1999 to August 2001. He was an assistant professor at National Central University, Taiwan from August 2001 to 6. And he then joined National Tsinghua University as an assistant professor on August 2006. Currently, he is a professor at National Tsinghua University. He is engaged in researching transiting exoplanets. So I am welcome to Professor Ing Gyu Jiang. Yeah, please share your screen.
Thank you. Thanks for Da Vinci's introduction. I think I share my screen already. Now I open my PPT. Yeah. So So is the slide already show can be seen?
Yes, it's on.
It's on. Okay. Thank you. Thanks for the organizers, particularly I think she La and Devenja, and nice to know your institute, and also 24-inch telescope is going, is working, and thanks for the invitation to be with you for this nice symposium. Let me introduce what I have been doing in my with my group members. Basically, I spend most of my time on this exoplanet study. So the title would be Exploring Exoplanet Physics Through Transient Observation, which closely fit the topic of this symposium today. And I also would like to show some collaborators and co-author of my transient papers this several years. For example, my current postdoc, David, is from many of these actually from India, some from Thailand, and also from Ukraine, and etc. Israel. Some are working at Tsinghua with me. Some are international collaborators. I just give you them credit that they actually very nice to work together and to apply telescope time together, and sometimes write papers and make them publish. And basically, I will give a brief introduction about discovery of exoplanet, as maybe most of us are not really specifically work on exoplanet, because small telescope can also work on any kind of time domain or variability astronomy. So I'll give a brief introduction, and basically, after that introduction, basically I will show the network of telescope we use. Then we will talk about some of our results, which we publish or ongoing, mainly on the monitoring by transient observation, monitoring this star with hot Jupiter, and also a bit statistic data on the multiple planet systems. This is our solar system. There are many planets, and it's amazing that you know, about 30 years ago, we know that there are other planets around other stars, which just 30 years ago, compared to the history of astronomy, is really short. So it's exciting news for most of the astronomers. Then the first one was this hot Jupiter move around the star 51 Peg, and it was awarded a Nobel Prize a few years ago. They used a double shift method, and in addition to single planet system, actually this method based on double shift is called radial velocity method in this field. It based on the oscillation period of the radial velocity. You can also confirm some multiple planet in one system. For example, Observational Andromeda is very eccentric because in terms of inclination, some of inclination of this planet is very high relatively, and there are 3 non-planet. So it just show you a case that very diverse systems can be discovered, and this is one of the reason that the whole field becomes so popular and become one of a major quickly developed field in astronomy. and also trigger many major effort in the planet formation, no matter in theoretical world or those you can see those AMA observation of protoplanet disks. Also, really would like to address the planet formation. All this really triggered by the discovery of exoplanet, and also once you discover, you try to understand the property. That's why I call it exoplanet physics. And tracing is, I would say, is the second method, and is very important because the first tracing for exoplanet actually was better for a system that already detected by radio velocity, so it's a double confirm. Astronomer was really exciting because even a radio velocity method is a sort of a indirect method, and when you have one more method, tracing method to double confirm for the same system, it's really exciting, and the orbital period and the property of the orbit by both radio velocity and the tracing are consistent. And after that, the tracing become noticed, and then more and more astronomers just try to use small telescope because tracing can be done by small telescope, and many survey projects start to build up a network of telescope to make more discovery. This is just to show you that simple tracing light curve can actually give you many information, including the depth and the width of this light curve. And this is a Kepler radar. Kepler, as we know, that's one of successful space project. Now the TESS test is taking on, is ongoing. Both ends are many from NASA also collaborate with a few others in the world. Because the high precision of their photometry, so they can detect many like super Earths, etc., to increase the number of detected planets to be thousand, to be at that time first of their paper to suddenly become 3,000 exoplanets. So most of them by Kepler. Now we know a few months ago NASA announced it's already 5,000 in total for all the exoplanets being detected. And however, I would like to show you this cheapest one. Is one of the actually it's the exoplanet system with more the 7, right? At least 7. So it's the system with many more number of the largest number of planets among all these detected multiple planet system. And I just checked the website. Actually, CHEPS-1 has 2 telescopes from a network. Actually, a small telescope is 24-inch. So really, 24-inch can make great discovery because this system is so well known that there are the number of planets is the largest. And yeah, it's not by space telescope. It's not Kepler radar. It's ground-based radar. So, and just show you that those green dots are this is on the period and the mass plane. The green dots are those detected by tracing. So they tend to detect the small period planet. But for radio velocity, they can detect the planet with slightly larger period. Those with red dots are radio velocity detect object. So let me show you the network of telescope. The main scientific goal at that time was to monitor the stars with Hot Jupiter non-exoplanet. So at that time we do not think we would have enough telescope time to do a big survey. So we start from small amount of telescope time. So we decide to monitor a non-transient planet as a first try. So for non-system, you can just produce new transient light curve. And for example, I will show you the light curve later. So from the light curve, you would determine the mid-transient time. Then the timing would tell us some information about the orbital evolution. So the top two panels just show you that the left side is just the case with two body, but everything is fixed. I mean, in terms of orbit. But if they are close enough, massive enough, the orbiter might experience enough tidal influence, and orbit might shrink, might change. Although is very slow. Another possibility is if you have a third body in addition to central star and the transient planet. If there is another body, then your transient might come slightly earlier. Okay, so three body or slightly late. This is what we call TTV. Okay, transient timing variation. But in general, TTV become unexpectedly getting a lot more people to work on it. So of course the orbital decay also, as long as the timing is changing, we call it TTV. So any particle physical reason can be considered and checked, but the most popular are these two, and which we our group consider these two cases. And this is the telescope that I try to contribute CCD camera for example, the Crimea one. We purchased CCD and shipped to Crimea, and it was already a while. And as you might heard, that Crimea was invaded by Russia, and now not only Crimea is a war there. So I sort of just a difficult time to get contact with them. And however, in the meantime, I have Indian friends, collaborators. So we have able to use Aries telescope, and we did get a proposal of HCT 2 meter in Indian, get proposal approved and get the time and get the data. And we also use WISE in Israel. We also have PRC collaborators, and we also have those two in US. And some of these we sort of stop having access, but we are considered new one for them. Recently, I have a good Thai student, so we are using the Thai test more heavily recently. So in terms of test time, for a long-term project, some might just gradually lose the contact, but we will consider a new cooperation too. So this is the almost the first one we try to use, and this is telescope inside the dome, and our CCD is here, and was attached on a telescope. And this was the Crimea people sent me a list of their number of light curve on different exoplanets. But however, I my postdoc make a list that combined with other telescopes, like just count a number and then make a summary. And so Creamier has able help us to access 3 telescopes actually, although we only give 1 CCD to contribute to this RC800, and we have other telescopes to use. And at that time, we sort of correct all this. Then we check literature, and based on the number of transient light curve, then we consider to address some scientific problem. So, for example, our first paper was this one, already acquired 9 years ago, and we have 5 transient light curve. So from the mid-transient time, we can address the TTV case I just showed you. And actually, the solid curve is the fitting model based on the orbit. So the transient light curve also can constrain the property of the orbital element of these systems. And just a more recent paper is this one by my PhD student who just graduated. So this is another case that you can see this O-C plot, and it's the timing subject by the case with fixed orbit. And if no TTV, then all the points should just lie on the horizontal dashed line. But actually, observation data will show you some up and down variation. Usually, you try to fit with some search some possible periodicity. Then if it's a more obvious periodicity, you might find more confirm the additional planning. So but however, for this case, in terms of the power of this frequency fitting is not high enough. So the conclusion of the paper is that there is no periodic oscillation. However, some variation seems to be there and not be explained well. But I think the collaboration with my former postdoc from India now, Parija is now working as a faculty in India by another paper recently, and repeated this target combined with the TESS, TESS data, and confirm this non-periodic confirm these variations still there. And for this was 43, which is a case that at that time, the left curve is a curve with a larger curvature. So before our paper, there was a paper claim already claimed was 43 might have some orbital decay. So we just provide some new data on right hand side. Okay, new mid-transient timing data, and this would using the same orbital decay formula, we provide a new orbital decay rate. And so our orbital decay rate was quoted by this theoretical paper later on. So however, about the same year, also another paper worked on the same system with an even smaller orbital decay rate. So somehow this system was attract a lot of attention, and of course this system might need a long-term monitoring. Our paper was a while ago, so we obtained a new orbital rate at least at that time, and I think this target probably still will continue study. Although I think there's a recent paper combined with the test data to claim that probably, yeah, the decay rate is really small, and this target somehow also is in the early signs of GWST by other astronomers. Though I do not always involve those big project, but so for this system, my PhD student, she recently, just this year. So this is a case that we have a more sinusoidal variation, TTV, and probably the possibility of existing of additional planning is there. And for multiple planning system, and the nice thing for Kepler is, several thousand of planets were detected. So of course they would like to make some conclusion from their statistic data, and they found that for multiple planet system, it seems that the nearby, or for the same system with several planet, the size are so similar, and the spacing are regular. And this reminds us that for our group, we have some study for multiple planet system. We found some PD ratio, mass ratio correlation, which is different from those their result on the multiple planet system. However, it's definitely related because we study the mass, for example, PD ratio on one axis, mass ratio on another axis. For adjacent nearby planet, it seems there is a correlation. But if you randomly pick two planets in a multiple planet system to calculate the ratio, but the probably look more random. So it means that probably the adjacent planet does influence each other during their formation, and which probably also connected with those Kepler data that those planets in the same multiple planet systems have a similar size, although a lot of detail need to be addressed further if we have a good future student. And conclusion, more than 5,000 exoplanets are known, and we have constrained some of their orbital changing rate, and we give some implication for possible addition planet, and also PD ratio, mass ratio correlation. Correlation coefficient about around 0.5 is moderate, but still in astronomy probably still worth to study. And in the future, we hope to start to consider to spend more time to study multiple planet system. We also will combine public available, publish, and also test data. It is really time to further characterize and study exoplanet, which make us understand how ourself, our life, and our Earth form. And really, you are welcome to observe and work together. And as you see, we do. It would be nice to have a more testable time and more people, more good active researcher and student to study together. Okay, I will stop here. Thank you.
Thank you so much, Professor Jian, for a nice talk. Now it's time for a few questions. Yes, Ritika, you can ask your question.
Sir, you mentioned that you found some evidence of orbital decay in WASP 43b. So, if there's an orbital decay, the planet is kind of moving closer to its host star, and as a result, its gravitational interaction will also increase. And since we know that hot Jupiters cause some tidal spin up, so can this and now that we have tests, can we confirm it, or like can we check if the rotation rate is increasing in the host star?
Right. So yeah, are you asking some detail of the interaction between star and the planet, right? And so yeah, once they are closer, the gravity is stronger, and so you but however, the fitting really just use a simple parametric fitting. Okay, so just assume that the there is a curvature as a function of apple. Apple means uh, different changing event, and the usual fitting will be like linear with straight line, and those with another third body we use sinusoidal, but for orbital decay, then you have another nonlinear term. And but however, for complete theory, really this parametric formula is not enough. And at later time, I think the particularly yeah, I think you mentioned the spin. Okay, the spin does matter. If your central star spin fast enough, I think even the tidal interaction is strong. The planet might still keep the same orbit, or even expand orbit. But even in the case that the star spin is smaller than the orbital period of the planet, then according to theory, the orbit will become smaller and smaller. And this is just one of the theoretical aspect one should improve and to get a detail of this model. And another aspect is the distortion. Okay, I think one of these hard Jupiter system was observed to have a non-spherical shape for this hard Jupiter. Okay, for that case, the orbital evolution also very interesting. So, did I really answer or touch your point?
Yes, but like I just wanted to know that can we correlate this orbital decay with the rotation rate of the host star? So, like, can we check if the rotation rate is actually increasing because of the
Oh,
orbital decay?
yeah. Okay, so you are asking, can we know? So, so yeah, I think you are right. During the interaction, the stress spin might be spin up, right? Because the companion goes in. Theoretically, yeah, we see those theoretical data and from the book or from paper, but observationally, so without planning, I think to study the rotation, one probably uses spectrum light to see the rotation velocity. Yeah, appreciation detail. How to measure? I'm not sure, but I think one should be able to know more about.
Speaker, you can send mail to speaker if you have more queries. Okay.
Okay.
Right. We can get some more detail. Yeah, it's
Yes.
mostly about the observation. How can we measure this observationally? Yeah.
Yes, thank you.
Okay.
Is there any questions? Okay. If no more question, then let's thank the speaker again. Our next speaker is Dr. Priya Hassan. Is an assistant professor in physics at the Maulana Azhar National Urdu University, Hyderabad, India. She did her integrated masters from the Moscow State University, Moscow, Russia, PhD at Osmania University, Hyderabad in 2004, and postdoctoral research in France and Ayuka, Pune. She was awarded the Women Scientist Award by DST in 2006. She has presented her works in various conferences in India, Europe, and the US, and in the United Nations, Vienna. Her research interests are in observational astronomy, star formation, star clusters, and galaxies. She is actively involved in Olympiads, public outreach, and science popularization programs, and has worked on various projects with the IAUOAD, US Consulate Hyderabad, etc. She is the co-chair of Women in Astronomy, WGIAU, and a member of the TMT ISDT on formation of stars and planets. So I welcome to Dr. Priya Hassan to present your work. Yeah.
Thank you. Thank you so much, Devendra, and thank you for inviting me. I hope you can see my screen well, right? All good?
Yes.
Yeah. Okay. So thank you so much. And today I'll be talking about the power of small telescopes being the theme of this meeting. And I'll be focusing on the 40 centimeter LCOs. So the LCOs, we come to that, is basically a set of telescopes, robotic telescopes, at 7 sites around the world working together as a single instrument. Now, so what do we see? What is LCO? You can see the positions over here. You have 7 positions where you have these at 7 sites. So you can see 1, 2, 3, 4, 5, 6, 7. Yeah. So you see the green ones. Yeah. And what you can see is the yellow ones are the offices, but these ones are the things. So there's basically a network of astronomical observatories run by a non-profit, and the telescopes are evenly, well distributed in the northern and southern hemispheres. Like you can see, they are 14 centimeter telescopes, which look something like this. So a typical site looks like something like this. And at a single site, you have more than one telescope because you have 25 at southern sites, and you have it distributed in some such a formula like this. And now, so what are robotic telescopes? Now, typically in today's era, when even when the institute who's organized this, you are talking about new institutes which have limited resources, or you have small telescopes, then robotic telescopes is a very good way out. Typically, for example, for Indian universities or for bodies or individuals who do not have access to very big telescopes. In this case, what happens is a robotic telescope like the LCO. It's a telescope that can actually make observations without hands-on human control. The good idea is that since these telescopes are located at 7 sites along the world, depending on what you want to observe, you can observe those objects at different sites, right? And if they are, different telescopes are automated to different extent. There's a certain extent which is available with the LCO, and you can schedule your observations using these telescopes. And so in that way, what happens is the observations are carried out automatically in a certain manner as you plan it. Now, what makes the LCO unique is typically if you look at the day-night curve, as you have the day-night curve taking place, you have all these different locations, 7 different sites, and they could have different conditions as well as because of the rotation of the Earth, there could be day-night at different positions. And what happens is you get a good global distribution of these telescopes. So you can dynamically schedule your observations at these different things in such a way that you can get round the clock data. So supposing if you have some event which you want to urgently observe, and obviously it's observable at different sites at different points of time, you can actually access it from these different locations by accordingly planning your observations, right? So, and the other thing about LCO is you get very rapid delivery of data. You can see that if you actually apply for observations within a day, generally, you do get your data, whatever data you apply for. So it is fast, it's robotic, and it's also processed to a certain extent. So this actually forms a global network. Many of the earlier speakers also spoke about networks But with networks, what happens if you have ununiform telescopes, different kinds of telescopes, then it would actually be quite a big trouble in synthesizing the data from these different telescopes, because all of them have characteristics of their own. What's done with the LCO, the Las Cumbres, is that all these telescopes have the identical instrumentation. They are identical telescopes with identical instrumentation. Obviously, the sky conditions vary, but for you to actually compare data obtained from telescopes at different sites becomes much more easier because of the uniformity in the kind of telescope. And so there are 40 centimeter ones, which I would talk about. There are also 1 meter and 2 meter telescopes, which are part of the network, but for which you need to separately apply for, depending on if you want to use it for a certain purpose. Now, each node, which I showed you, there's a cluster of telescopes on which you can do photometry, fast photometry. Spectroscopy is available on the bigger telescopes, and also photometry on the bigger telescopes. So typically, if we concentrate on the 40 centimeter telescopes, there is a camera, which is a 3K by 3K camera, which gives you a field of view of 20 to 30 arc minutes. There's also another fast camera for auto guiding with a field of view about 10 arc minutes. Okay. And there are 5 filters available which you can use for your observations. Now, what LCO does, or Las Cumbres does, is for the observations which you do, as part of the data, when you actually retrieve the data, it actually passes us through a pipeline called the Banzai pipeline. And Banzai is basically it's an acronym for Beautiful Algorithms to Normalize Zillions of Astronomical Images. So what does Banzai do? Is that when the telescope observes the objects, whatever objects it observes, immediately it's shipped onto the headquarters. And from the headquarters, it actually goes through the Banzai pipeline. The raw data goes through the pipeline. You get processed data, which is then sent off to the LCO archives. So then what happens is the user directly accesses the processed data. So the user does not have to bother at all about the processing of the data. So it also gives the advantage that, for example, typically for amateurs or even other astronomers who don't want to go into the detail of how to do CCD processing and various things like that, you needn't spend effort into that. So what the Banzai pipeline does is that for the data which it gets from the CCD, it basically does the standard procedures. The standard procedures are bad pixel masking, it does bias subtraction, it does dark subtraction, it does flat field correction. So it does, that is the basic CCD processing, what it does. And after that, it also runs it through a source extraction software, which is very similar to Source Extractor. So this SEP is a source extraction software. So you actually end up with a catalog. So while you have the images, you also have catalogs, and as well as you can do as you have astrometric calibration also. So the end user gets the cleaned images as well as the cataloged images. For example, if you're looking at, say, a cluster of stars or some sources, you will directly get the source extractor kind of output from that thing. So what happens is the Banzai pipeline, the end product, when it gives you an array of pixel science data, okay, which is the science data. It gives you pad pixel masks. It gives you the array of cumulative pixel uncertainties, and it gives you a catalog, like I mentioned earlier. So a catalog, what does it do? It gives you the pixel positions, the X, Y, the semi-minor axis, the position angles, and some basic information about each of the sources which you have, right? So in principle, it processes all the data, gives it to you in a processed form, which you can directly use for whatever other work you would like to do with your data. Right. And then it's all put to the data archive. So if you go to the data archive at LCO, you can actually access the data archive and see whatever data interests you. So that is available to users. So what the LCO actually achieves is that it gives you world-class science defined by this. It's an engineering feat in the terms of this thing. It also plays a very important role in education, which I'll also talk to you about, is that how you can actually, typically for your institute or wherever you put this thing, if you're part of a club or whatever, you can actually organize education projects using the robotic telescopes. Now, one of the main, the real work of the using the LCO is for time domain astronomy. So typically, because you're going to have global coverage of any event which is taking place, you can actually do time domain astronomy very well using the telescopes. So, for example, there is the example of the first kilonova. So, if you remember sometime back, this would be, say, in the year 2017, right? This was in the year 2017 when there was an alert given on a neutron star merger by the LIGO observation. This is the very one which gave them the Nobel Prize. So, there was an alert sent that you have this neutron star merger taking place from LIGO data, gravitational wave data. Now, based on that data, you basically had it from three different sources. So they could actually pinpoint the source, but pinpoint the source to an extent of 30 square degrees. So for 30 square degrees area, they could say where is the source sitting, which is connected to this. Now there were six different groups which are actually trying to look for the source of this LIGO source, and the LCO, which includes the LCO telescopes. So what they did is they actually scanned the data for galaxies in that area, which could be possibly giving them this data. And this is about the fifth or the sixth galaxy, which they were actually potential this thing, which turned to be the true source of this thing. And this is called a kilonova, which is like a supernova, which gave out this burst. And you actually have, so initially what happened is the Fermi satellite detects this gamma ray burst from a thin area, from this area of sight, which is this sky. Then the LIGO and Virgo detectors, they triangulated. They found the location of the source within this area. And then LCO played the very important role of identifying the source of this gravitational wave source within this area, which is of 30 square degrees. And this was the kilonova over here, which they identified over here. This is in galaxy NGC 4993, and here's the kilonova source over here. And just to give you an idea, this is a very large area. This is a 30 square degree area. This is a half a degree area, which is the size of the moon. So what they actually did is identify this source. And the problem with this kilonova is that it became red and faded in a very short period of about only in a few days. And therefore, it needed to be monitored in a very, at a very regular rate all the while globally. And that's exactly what the LCO telescopes did. So they monitored this source very well and characterized the source very well, for which they actually obtained the spectrum and many more details about this source, right? Another important contribution of LCO is with exoplanets. So there is actually an LCO program of detecting, studying exoplanets using microlensing, using transit method, as well as using the radial velocity method. I won't go into the details because the previous speaker just spoke about exoplanets and the various methods. So, for example, there's an there's an LCO instrument which has been funded by the Isaac Simmons Foundation, which are basically going to monitor uh, monitor these exoplanets, these super Earths, and these are basically the alert was got from test data. So from test data, we knew about this object, and including data from the University of Liège as well as the test follow-up team. This is also a potential for James Webb, but before James Webb does its job, LCO can actually do a very good job of monitoring this source so that it is all ready for James Webb to then characterize. There's also an exoplanet watch program which is run by with LCO, which is a citizen science program. So this includes people who are non-astronomers who can actually observe exoplanet transits, because what you can actually do with LCO telescopes, you can monitor a certain a certain host star and actually monitor that this thing. So basically, what happens is this is like a precursor, or it's like the the initial observations, which can then be used for bigger programs on bigger telescopes. So what you can do is one can actually characterize exoplanets, get their time periods to better accuracy using LCO telescopes, right? And then bigger programs can be planned using bigger telescopes with the candidates which are identified using LCO, right? So there's a whole big program on exoplanet watches using that. Another interesting thing which I wanted to show you is many of you all would be aware of the DART mission, which took place very recently. And what the DART mission actually did is it was NASA's experiment to test whether can we actually save the Earth from an asteroid impact. Okay, so there is the asteroid system called Didymos, and which has a binary which is called Dimorphos, and the DART mission actually impacted Dimorphos. And what was done is that there was monitoring of this impact to see what is the change in orbit of Dimorphos, which is obtained by the impact mission, so that one can actually characterize and say whether this kind of a method for saving the planet, can it be effective? Can it actually do its job? So what actually happened is, this video is not working. Oh, it will work over here. So I'll show you how this was a group led by Tim Lister, who actually, and this group, using LCO telescopes. If you can actually see, I hope this works. Yeah. So I hope you all can see it. There is the impact mission, and you can see here's the impact mission, and it has been very beautifully captured by LCO telescope, the 1 meter telescope. Okay. So various telescopes around the world were trying to monitor it, but obviously there was a problem about the time of observations. But with LCO, there is a possibility of having a continuous monitoring of this thing. So here's the impact. Here are two images, which actually show you how well the impact. So even now, there's constant monitoring of this object to basically study the motion of this binary asteroid system to see whether the impact has actually been successful in, in actually changing the orbit of Didymos in this double system. And can this be used as a potential method by NASA to actually, and various space organizations, to protect the Earth from asteroid impacts? Another important thing I would like to talk about is LCO is also very effective in using it as an educational resource as well as for citizen science projects. So as an educational resource, we ourselves, we have a group which we run, which is called Srishti Astronomy, and with me with SN Hassan. And we actually, LCO has what is called the Global Sky Partners Program. So you can, ideally speaking, as an institute, as an individual, at whatever level you want, you can propose to be a Global Sky partner to the LCO telescopes, which basically means you will have access to their telescopes at all time. So at all time, you can try to get observations of any object or anything which you are interested in using the LCO telescopes, and thus get, first-hand experience of using this thing. So for example, there is one which is called ExoClock, which is actually looking at the ephemeridus of aerial candidate exoplanet targets, right? There's another one on exoplanets. There's lots of work which people are doing even with variable stars, because variable stars, you have to just keep monitoring them at different cadence by different gaps. And depending on that, you may actually be able to identify different kind of sources with different kinds of variability, intrinsic as well as extrinsic variability, which could be interesting. So a lot of schools, colleges, etc., can also get involved into these kind of projects, because the data which you're getting from LCA is already processed. So students or participants do not need to know how to use CCDs. They don't need to know how to use, how to build catalogs, etc. They already have processed data which they can use for their purpose, for whatever is their scientific goal. So at Srishti Astronomy, the project we proposed is on star clusters. And basically what we do is we do observations of star clusters, and with the LCO telescopes. And there are many more. I can, if you click on this, you can actually see, this is a link to the LCO website, where you can see the Global Sky Partners website, and you can see there are a whole bunch of different projects which people are doing with LCO telescopes. You can have a look over here, and there are many more details. I just mentioned a few, but if you scroll over here, you will find a whole lot of different projects that people are trying to do at different levels. These are school, college, university, citizen science, all kinds of levels where people are trying to do projects. Okay. So I will just talk a little bit more about our project, which is the Srishti Astronomy one. So the project is basically educational, and the idea was to teach people the fundamentals of observing, of planning observations, of doing photometry, of what is standardization, photometry standardization, what are star clusters, what are HR diagrams, how can you use Gaia and other data sets along with this, as well as what is the science you can do with HR diagrams. So what we basically did is, this is our page, our Global Sky Partners page for Srishti Astronomy. Like I said, it's led by two people here, and we are at the Maulana Azad University. And what we do is we do in-person. We have not done in-person workshops. We'll be doing one next month. But otherwise, thanks to COVID, we've had a whole set of online workshops where we've tried to, explain to people these various concepts. So here you can see examples of our workshops. We had one last year in October on the HR diagram with LCO, which was this. We did one and we did two. here where we actually showed them how to do photometry, how to do aperture photometry using LCO data. That is, we taught them how to use the aperture photometry tool, APT, as well as TopCat, and how to plot HR diagrams of star clusters. This was the HR diagram with LCO. The second workshop we did was using the Banzai pipeline. How do you use the Banzai catalog to actually build your HCO, the LCO data? And then we had another recent workshop, which was last month, which was basically on photometry, which explained what is the basics of photometry, what is the Banzai pipeline, how do you actually plot these things and do it. And here's an example of registration for our workshops. So you see that we have people, because of the COVID effect, the online effect, we had participants from all over the globe. We are located here in India, but you can see we had participants from all over the world who participated in our workshops and could take part in this. So this is also being done in collaboration with the OAD as well as Shrishti Astronomy, which is our home organization. So here I think I hope I conveyed to you how the LCO telescopes can be used for various science cases as well as for educational purposes, for training students, and many more things about that could be very effective. And hence I would urge participants, either if you'd like, you can get in touch with us if you want to use the LCO telescopes, because we are already Global Sky partners, we have permissions. Otherwise, there's a yearly call which comes out sometime in the month of July, where you can apply for Global Sky partners, and then you will have access to all their 40-meter telescopes. And you can do a whole lot of science cases, science programs with these telescopes. And I think that really genuinely gives people the feel of observations and the fun of acquiring data and analyzing. So thank you. I'll stop with that. I'll be happy to take questions.
Okay, so we can have at least one question. Yes, Raghav Krishna.
Hello, ma'am. This was
Yeah.
an inspiring talk. I have one small question. Is it possible to observe high redshift galaxies using LCOs?
Okay, so obviously the brightness limit that you go to, because the telescope is small, it would be obviously difficult. In principle, I think it should be. The thing is, you can stack images and do things like that, but in principle, I would say it would be difficult. It is.
Okay, if photometry is not possible, is it possible
It,
by
one actually,
spectroscopy?
Yeah, so spectroscopy is only available on the 1 and 2 meter telescopes. The ones I was talking about was the 40-meter telescopes. That's only photometry. So one actually should try it out. It depends on the brightness. What is the brightness of your sources?
About 29, 27 magnitude.
Oh, no, no. Then you even with James Webb, it would be difficult for you. I mean, it would be possible. So this is not meant for these. Sorry, you won't get.
I think you can discuss later because we have another speaker and she has
Yeah.
something also. Thank you.
Okay.
Thank you, ma'am.
Yeah. Okay.
So our next speaker is Dr. Archana Som. She mainly works in galactic star formation and roles of magnetic fields in that process. She did her PhD from Aries in 2016. After that, she moved to Korea Astronomy and Space Science Institute in South Korea for her first postdoc. Then she moved to NASA Ames Research Center as a National Science Foundation Fellow in July.
Ashish, I think you're frozen.
Hello.
Devendra, can
Yeah,
you hear
yeah,
me?
Archana, yeah, you can share your screen. Actually, there is some
I
network
think
issues.
I'm not able to share. I'm not able to share because the previous presenter is still sharing.
Oh,
It's back now.
Dr. Priyasan, can you please stop sharing? Hello.
Priya, you there?
Hello.
She's not here. And can someone can moderator unshare the screen? Can you guys do it? Okay, I think I'll do it now. All right, I'm trying to share my screen. Okay. Can you see my screen? Can you confirm?
Yes, 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 yes. Yeah.
Now I'm going to do a full screen. Can you see the full screen mode?
Yes, yes. It's fine. Yes.
Okay, yeah, good. Thank you. Yeah, good afternoon, everybody. And thanks a lot for giving me this opportunity to show my work on the roles of small telescopes in many exciting areas of observational astronomy. Actually, I started as an optical astronomer, and then I moved to the different regimes of electromagnetic spectrum, like near infrared, some millimeter, and radio, in my different postdocs in South Korea and the US. And recently, I joined IE as an assistant professor. But in this work, because it's a short talk, I'm going to focus on the science done with the 40-inch telescopes, as well as the other small telescopes, in finding the roles of magnetic fields in the star formation at different scales. So magnetic fields play an important role in the formation of stars and the evolution of overall interstellar medium, what we see around us. Outline of my talk will be that I'm going to show a little bit of overview on the importance of magnetic fields. Then I'll say something about the problems addressed in my research, and some findings and some takeaway points. So before moving into the different science cases, let's stare at this slide and find out why magnetic fields are important in the ISM. So actually there is a broader picture of star formation where it gets split into two schools of thoughts. One is that magnetic fields are important in the formation of stars. Okay, formation of star, here I'm talking about the sun-like stars only. And the other school of thoughts says that the turbulence is important in the formation of stars. In this presentation, I'm just talking about the magnetic fields, interstellar magnetic fields. So magnetic fields observationally, as well as in different types of simulations, are found important in regulating and resisting the charged particle flows across the field lines. And they give kind of mechanical supports to the different structures where stars form. Just to begin with, stars forms in the clouds of molecular gas and dust, where dust is 1/100th time of the gas. So our interstellar medium is overall vacuum, but we have a lot of gas around it. And then wherever we have these molecular clouds forming, there we have stars form. So magnetic fields also helps in solving the angular momentum problem in star formation. I'm not going deep into details of angular momentum problem because that's a separate regime. It also regulates the energy flows at different scales. In different galaxies, also in the molecular clouds, it has been seen that the outflows come out of these structures and they are parallel to the magnetic fields. So magnetic fields kind of help the material channel out from these small and large scale structures. They play important role in the dynamical evolution of the star forming region. Dynamical evolution, I'm saying, in terms of when molecular clouds form and when they evolve to the verge where star formation starts. So magnetic fields are found playing important role in this overall evolution of these star forming regions. So if we are able to do polarimetry of the interstellar medium, we will be able to map the magnetic fields, and also we'll be able to estimate their strength in the interstellar medium. And there are many papers and many annual reviews written on why magnetic fields are important in annual review by Dr. Christopher Mackey and O. Stryker, that they said that B fields are found. B fields, sometimes I'm saying, are the magnetic fields found preserved in the formation of molecular clouds. So, as I said, if we are able to from different telescopes using the polarimeters as back-end instruments, we'll be able to map the magnetic fields in the interstellar. The question is, how do we interpret the magnetic fields in the interstellar medium? And the answer is polarization of starlight. And that polarization different regions of electromagnetic spectrum. So what is the idea behind polarization? So light coming from the interstellar medium, light coming from the stars through interstellar medium is found polarized when it is seen through the polarimeters. And what is the reason behind the polarization of this light is the interstellar dust. So interstellar dust has elongated And when those dust grains are hit by the inhomogeneous interstellar radiation field, they start spinning. And they get aligned with the magnetic field lines in such a way that their minor axis is parallel to the interstellar magnetic field. Okay, so now you have a picture where elongated asymmetric dust grain, which are mostly made up of silicates, are aligned with the B fields, and their minor axis, the minor axis of this elongated dust grain, is parallel to the B field. So suppose whatever light is coming from the behind these aligned dust grains, that gets partially polarized because a component which is perpendicular, which is parallel to the longer axis of the grain, is get extincted more than the component which is parallel to the small axis of the grain. So at the end of the day, we get a little partially polarized light because one component is absorbed more than the other component of the light. So this is like grain alignment theories itself is a big research topic in our region. So I'm not going to talk a lot about how the grain alignment happen and all. So I'm just saying that give me a region in ISM where grains are aligned with the magnetic field lines. I will give you polarized light, and using the polarized light from in these telescopes, we can estimate the magnetic field strength. Also, we can map the magnetic field orientations in different parts of the ISM. Okay, so this is the whole theory. Okay, dust grains should be aligned with the magnetic fields, and whatever light we get is polarized. So when we get polarized light from these telescopes, from the interstellar medium, so using the polarimeters and using half wave plate, which is a retarder in the light what we are getting, we can estimate the Stokes parameters. Stokes parameters, which are known as QU, I, Q, U, and V, represents the overall state of the light. So I is the total intensity, Q and U Stokes parameters represent the linear polarization of the light, and V represent the circular polarization of the light. Whatever we see in these from these telescopes, or what I'm going to show here, is mostly linear polarization, and I'm representing that as from Q and U. And from those Stokes parameters, you can easily calculate degree of polarization, which is P, and also polarization angle, which is theta. So polarization angle at the end of the day is nothing but the angle of the magnetic field in the interstellar medium. So if I give you a lot of Stokes parameters towards a lot of regions, you are able to estimate the P, and you are able to estimate theta. And that theta is nothing but the angle of magnetic field in that region. So you have theta information now. So you know what is the orientation of magnetic field. So I just gave you a broad picture that, okay, how we get the magnetic field orientations. So now let's look at the status of the polarimetry. We do polarimetry in all the electromagnetic wavelengths now, mostly, and the dust polarization in 850 micron was very nicely represented by this Planck satellite. So where they did all sky polarization, dust polarization mapping in 850 micron, and they revealed the magnetic field structure, all sky magnetic field structures, where these lines, in the striations you can see in this picture are nothing but the magnetic field orientations in the galactic plane, as well as on the different latitudes of the galactic plane, of the galaxy. So most of the time it has been seen that magnetic fields are perpendicular to the elongated dusty structures. So these elongated dusty structures are nothing but the molecular clouds where stars form. Okay, so these are the locations what I was talking about. So Planck in the left picture in here, torus. So Planck measured the magnetic field orientation and strength in the torus, and they found that most of the magnetic field lines are found perpendicular to the elongated filamentary structure of torus. Then it has been seen in different other studies also, and IC 5146, another filament was found where magnetic fields were elongated, were perpendicular to the elongated structure of the molecular cloud. So this I'm showing here is because it is kind of a global picture now what we are seeing. So there has been so many surveys and so many studies towards ISM, these molecular clouds, and everywhere almost 80 to 90% of the regions we find that the magnetic fields are perpendicular to these elongated structures. So what we can infer from that is that B fields or magnetic fields are mostly perpendicular, and they play an important role in channeling the material and putting it together and making the molecular cloud filamentary. So there are simulations on where they were numerical simulations and where they were showing, they were kind of predicting that the filaments are formed by the magnetic fields. Now these observations are directly showing that the magnetic fields are helping the material to accumulate and form a filamentary structure. And those material, when they become gravitationally unstable in different locations, then they form star forming cores, and then subsequently small stars are formed there. So this was just an introduction. I just want to tell you a little bit about my observational journey, which I started with 1 meter telescope at Aries in my PhD. It is a 1 meter telescope with the aim pole as a back-end instrument. It is a polarimeter, and where we do a lot of polarimetric observations, mainly towards star-forming regions. But now people have started using it for observing supernovae, blazars, and AGNs, for finding the variability in the polarization in these particular sources. So in my journey, in my PhD, actually, what I did is I submitted almost more than 10 proposals at this polarimeter. We observed more than 20 star-forming regions to map the magnetic fields as well as their strength. Then we got observations of around more than 300 hours, because polarimetry is photon starved. So you can imagine that polarimetry needs a 4 times more observation time than the normal photometric observations, because you need a lot of good signal to noise at different rotations of half-wave plate. So you need a good signal to noise, good signal for finding the polarization. Otherwise, your polarization signal will be just lost in the noise. And we published more than 19 papers on using those data. So I started with polarimeter at 1 meter telescope in Sampunan and in Aries. Then I moved to South Korea and I started using JCMT, which is a 15 meter telescope, sub-millimeter telescope. It has a polarimeter as back-end instrument, and it gives you dust polarization in long wavelengths, that is 450 micron and 850 micron, that is far infrared sub-millimeter, which traces more cool dust. And then in my postdoc in the US, I was mostly working in this flying observatory where we had a polarimeter where we had a far infrared observatory, which works within mid to far infrared regimes, and it had a polarimeter for far infrared wavelengths. So it was a flying observatory, is to fly for 10 hours every night and then come down, and then next night it is again going for observations. So this was an exciting place for me, actually. So this was the journey from optical to sub-millimeter to far infrared. But these 3 observatories were not enough to compile everything or all the regimes of the star-forming regions because of the densities and temperatures. So I used other observatories also. For example, Serpol at IRSF in South Africa. I also used SMA in Hawaii and ALMA in the US. So these were the facilities I used. That was before facilities. I showed you the main idea behind using doing this research. So the questions addressed. First question I addressed in my research was on galactic magnetism. That was the main motivation, and I wanted to see how scales and environments of these star-forming regions or these molecular clouds are important. How magnetic fields are important, or how they differ in different environments and different scales. I'm showing you 3 pictures here. So left one is the pillars of creation, which is also known as M16. Right one is right 2 pictures are the 30 Doradus and IC63 star-forming regions. In all these 3 regions, we did magnetic field morphologies, polarization observations, and magnetic field morphologies and magnetic field strength estimation. We found that pillars of creation, which is highly affected by the high energy radiation coming from the stars, a bunch of stars sitting in the northeast, they have a kind of effect on the magnetic fields, because all the magnetic field lines look like following these finger-like structures or the pillars. However, in 30 Doradus and IC63, the magnetic fields were affected by the radiation, but in a different manner. So magnetic field lines in 30 Doradus here looks like curved on 2 fronts, up and down, because of the radiation from this star here, which is an O star. And also in IC63, the magnetic fields were modified drastically by the radiation coming from the southwest, which is a O star sitting in there, B star sitting in there. So overall idea behind this slide is that magnetic fields do play important role in the formation of these structures, but they are also affected by the different environment conditions in these clouds. Then talking about the scales. Ashish or Devendra, please keep me updated about the time. Let me know. So, okay. So about the scales, this is a result taken from the polarization observations from Planck, from AIM pole at Aries, and from JCMT
So
submillimeter
you have 2
polarization.
more
So
minutes.
Planck. 2 more minutes. Okay. So you can see when we map the magnetic fields in different wavelengths and from using different facilities, we do see a change in the magnetic field morphologies at different scales. So this is also important. And if you have to find out the magnetic field strength at these scales, you will find there's a drastic change in the magnetic field strength from very large scale to very small scales. So this is another image I wanted to show here, is that there is a filament G34 which we mapped in different wavelengths, and we found that the magnetic field morphologies change drastically at different scales, and their strength also changes drastically. There are so many efforts. These were just 2 things, and there are so many like tens or more than 10 efforts for finding field morphologies in different regions. And these are also some examples where I am showing that the magnetic fields are mostly perpendicular to the main cloud structure, which is recently published in FJ. So there are also hints, observational hints, where we found that the magnetic fields are helping in accreting the material and going towards the core inside the filament where star is to be born. Okay, so magnetic fields are helping in accumulating the material. This was the Nature Astronomy paper published in 2020, and this was first observational evidence based on the similar prediction done like many years ago. But strength, talking of strength, so magnetic field morphologies are not only important, strengths are also important. So for that, we need a density of the region, we need polarization observations, and if we have density, polarization observation, and velocity information, the gas velocity information from the radio spectroscopy, we can easily estimate the plane of the sky magnetic field strength. And using the plane of the sky magnetic field strength, we can compare, or we can find the competition between different energies, for example, magnetic energy, kinetic energy, gravitational energy, and thermal energy in these regions, which is important. If you don't know the energy budget of any region, you won't be able to understand whether star is going to form there or not. So that's why the comparison between all these energies are important, but magnetic fields play important role to know what is the contribution of the magnetic energy in these regions. So my student Yannick, he's a grad student in UCLan in UK right now. He did a lot of comparison of different energies in different regions. So before takeaway points, I just want to highlight this slide here, that a lot has to be taught to our young generation and also the people, also students who are interested in doing the astronomy, that we have a lot of facilities in India now, 1.3, 3.6, 1 meter Aries, 1.2 meter PRL, 2 meter HCD, 2 meter IGO, IUCA. And there is a drive going on right now that we should have a national collaboration. We should teach our students why and how to write the research proposals, what are the requirements and for the preparation of the proposals for different observatories, and how to write the scientific publications when you get the data. So national collaboration is necessary, and we should keep on teaching our students directly or indirectly that we have a lot of facilities already available, just make use of it. And with that, I want to thank you all with some takeaway points that magnetic fields are found important in the formation and evolution of the molecular clouds. And there is a lot of evidence seen that the radiation is able to affect the magnetic field lines. And different observatories, right from the optical to sub-millimeter, are producing results and giving you the information that magnetic energies are important in the formation of stars. So yeah, I'll be happy to take questions.
Okay, so you can ask question.
Hello, ma'am.
Hi.
Am I audible?
Yes, you are.
I have a doubt. You said these different different Stokes parameters images, I, Q, and how do we actually get the magnetic field orientations and strengths using these images? Are we going to measure the fluxes in each fixed file?
No. That's what I said in there. Once you have 4 Stokes parameters, I'm not going to deep into detail that how we measure it. You have to rotate your half-wave plate of the polarimeter to get these Stokes parameters. Once you have Stokes parameters, for example, you have Q and U, with this formula here, P is equal to 1 over I, Q square by square root of whole, and theta is equal to half of tangent inverse U over Q, you can get the P and theta. So this theta is nothing but the orientation of magnetic field. That's what I was saying here, that light is polarized in such a way that the polarized component is parallel to the magnetic field. So angle of the polarized component is nothing but theta. So if you have theta information, you have magnetic field orientation information.
No, what I'm asking is U and Q refers to Stokes parameters. How do we actually measure each Stokes parameters? That is in what units?
Okay. Yeah. So those things are, I did not write those equations here. QU, these Stokes parameters are measured from the fluxes of ordinary and extraordinary beams what we get after the polarimeter. So polarimeter has these components of half-wave plate and the Wollaston prism, which gives you two components of light, ordinary and extraordinary. One has vibration in the plane of the sky, and another has perpendicular to the plane of the sky. So you have these ordinary and extraordinary images. You have fluxes of O and E. From those you can calculate Stokes parameter, which is like a unitless quantity, because you have a ratio. It's a kind of differential photometry of two images. I mean, if you want, you can contact me. I can send you whole process, all those equations, how we do that.
Okay, so let's move to the second question by Professor Chakravarti.
Yes, Archana, I have one question that you have been telling many times, that the magnetic field is important. Of course, magnetic field, generally what happens is magnetic field follows the velocity field. Okay, so generally this is always the case, and therefore what by magnetic field polarization, what you are actually seeing is really the velocity field in the region. So that is point number one. Point number two is this case that you actually mentioned a couple of slides back, the table, where I see that the gravitational energy itself is factor of 10 or more. Yeah, here. For example, the gravitational energy itself, energy budget is 0.74 in the unit of 10 to the power 35, whereas magnetic field is 3.2 in the unit of the 10 to the power 35. So in this particular case, magnetic field is at least 5 times stronger. So this I am worried a little bit. The reason is, if the magnetic field is too large, then it becomes fluffy. It becomes like a blobby, because it has a lot of pressure but no matter. So it tends to become buoyant, and it tends to get out of the system if this field is so strong. So how is it that this strong magnetic field is getting confined into this dynamic system? This is a little bit puzzling.
Yeah. So thanks for nice question, Professor Sandeep. Yeah. So actually, this is a starless core. There is a puzzle about this region itself, is that this is at a very high evolutionary stage, kinematically, but it is not forming star. Most of the regions 1, 2, 3, 4, 5, especially number 3, it should have been forming star, considering the gravity and the density of the region when we compare it to the other cores, but it is not forming. So something is happening where the magnetic field is either responsible for this delay in star formation or stopping it. And so this is a starless core. This is why I wanted to, this is just one example I'm highlighting, but there are some examples where stars are forming and gravitational energies are much, much, much higher than the magnetic energies. And also, as you said, magnetic fields follow the velocity fields. There is another approach of finding magnetic field morphologies using the velocity gradients. So nowadays, people are not only using polarization observations. Now we are working on a technique where we have velocity information of different molecular clouds, and using the velocity gradient information, we are able to estimate the magnetic field morphologies or directions. So you're right. So when magnetic fields are found very, very strong compared to the other energies, for example, gravitational energies, in those regions, stars are not forming. So they are stopping it or for a long time.
Basically, the Lorentz force is so strong that matter is not following the Jeans instability, the criteria itself.
Exactly.
Even the Jeans, because the pressure
it is stopping
stopping from accumulating matter.
Exactly. So this
normally
magnetic
magnetic
example is the example.
Yeah, in this case, magnetic field is dynamically important to actually stopping the matter. In generally, magnetic field is a trace material, and so does not dynamically interfere. It only follows the generally the Euler's equation or something, Navier-Stokes equation. Whatever velocity field is there, magnetic field is just going to follow it. In this particular case, actually, it is dominating. So you should be able to see shock formation, shock formation due to.
This is a no. Actually, this is a very low energy region. This is a very low energy region. This is a very cold from core. Actually, we don't have any shocks or anything happening here.
No, no, but Alban velocity. No, no, Alban velocity must be very high. Alban velocity was supposed to be very high. Eh?
These velocities are of this. Okay, the magnetic fields here are of the order of 10 to 20 or 30 or 50 microgauss only. These are very cold regions, and yes, in the regions where we have bipolar outflows coming from the newly formed stars, there we may have these shock regions. So there, for that, we study the Hurwigger objects separately, magnetic fields in the Hurwigger objects. But these are very cold regions where we are just trying to find out what is happening, why star is not forming, whether there is so much magnetic energy is there, density is so much, it is sitting at the highest kinematically evolved state, but why star is not forming. So this was just one example. But I agree with your points.
Okay, so no more question? No, there is one more question.
Could you, okay, should I read it or?
Yeah, you can just see the question in the comment box.
Oh my God, this is not my field. I'm sorry about that. I have another meeting I have to run, but this is definitely not my field, like merging of two black holes. But maybe I'll think about it and I'll get back to you, Saurabh. Thank you.
Okay, thanks, Archana. So now let's move to the next speaker. Dr. Hartama Gaur.
Yes.
She is working as a DST Inspire faculty at Aries, Nainital, since June 2018. She completed her PhD from Aries in 2013. Then she worked as a postdoc at IUCAA between September 2013 to June 2014. Then she got Chinese Academy of Sciences Fellowship and did her second postdoc at Shanghai Astronomical Observatory, China, for the period of 2014 July to May 2017.
Thank you for my introduction. 1 minute, I will just share my screen first. I'm not able to share it. Why? So my screen is visible now? Hello?
Not yet.
Not yet.
I think you should share the entire screen.
Okay, 1 minute. Your entire screen. Chrome wants to share the. Yeah, I'm sharing the full screen, then the entire screen, but it's not 1 minute, 1 minute. What is the problem here? Your entire screen, share. Yes.
Yeah, now you can see.
Yeah, okay. Yeah, now it is visible?
Yeah.
Okay. So, good afternoon, everyone, and thank you for giving me an opportunity to present my work in this symposium. And I will talk about the role of meter class telescopes in optical variability studies of blazars. So the outline of my talk is, first of all, I will give a very brief introduction about AGN and blazars, and then I will talk about some projects which can be done using the small telescopes. So as we know that the big telescopes, they are always oversubscribed by many proposals, and so the small telescopes are easy to access, and when long-term monitoring is required, like in these type of projects, then the small telescopes play an important role. So I will talk about all these things. So here you can see that, so first I will talk about what are AGNs. So an AGN is a compact region at the center of a galaxy that has a much higher luminosity and that cannot be attributed to stars. So here you can see that the center is a supermassive black hole and it is surrounded by the accretion disk. So these objects are thought to be powered by the accretion onto the supermassive black hole which is residing at the center. So there is a these are the clouds which are called the broadline region. They are photoionized by the central continuum and they have high luminosities up to thousands of kilometers per second, and they are shown here by the black dots. So they are called the broadline region, and the gray dots, they are far from the black hole and they have velocities up to hundreds of kilometers per second, and they are called the narrow line region. So this entire system is believed to form, the obscuring torus is believed to form around the perimeter of the accretion disk, and it is thought to be responsible for the change in the appearance of the AGNs. So here you can see there are so many classes of AGNs, but in this talk I will just focus on blazars. In this schematic diagram, you can see that the upper half is a radio loud class where there are prominent jet in the AGN, and the lower one is a radio quiet. So an AGN looks different because it has different orientation with respect to our line of sight. So if we are directly viewing into the accretion disk, then the both NLR and BLR are visible in the optical spectra and it appears as a type 1. Whereas if we are at larger angles, so we are not able to see the closest part, this BLR, and only NLR is visible in the optical spectra, then these are called the narrow, they appear as a type 2. So the sources where we are directly viewing into the jet, they are called blazars. And so the properties of blazars are that they have flux variability across the complete EM spectrum. They have variable polarization from radio to optical bands. Their radiation is predominantly non-thermal, and the main property is that their jet axis makes an angle of less than 10 degree to our line of sight. So in this class of AGN, we are directly viewing into the jet, and hence we are just seeing the Doppler boosted jet emission. This is the spectral energy distribution of a blazar. So here you can see the SCD of a blazar is a double peaked structure. First hump peaks at low energies and second hump peaks at high energies. And the classification is based on the peak of the first hump. So if it is like new peak is approximately 10 power 15, it is greater than 10 power 15, then the class is HSP. And if it is less than 10 power 14, then the class is low synchrotron frequency peak blazar. And if it is in between that, in between these frequencies, then it is called intermediate synchrotron frequency peak blazars. Now the possible emission mechanism for these two peaks at low energy, we have the synchrotron, the possible reason for the low energy hump is due to the synchrotron emission, and at high energies it is not well understood, but it is usually explained as arising from inverse Compton scattering of the same electrons that are producing the synchrotron emission. So if these electrons interact with the synchrotron photons, then the process is called synchrotron self-Compton. And if they interact with the external photons that are originating in the local environment like accretion disk or BLR, then the process is called external Compton. So these type of sources are blazars are variable across the whole electromagnetic spectrum. This is a typical example of a light curve of a blazar. Here you can see this is a light curve in the radio band. So here you can see that it is much variable in this band, and they are variable in optical bands also, and hence they are very good targets for the optical observations. Now here this is a again schematic diagram. So here we are somewhere here. We are directly viewing into the jet. So here the colors shows the frequency stratification that when we are closer to the accretion disk, they are much hotter. The gas is much hotter. I mean, when we are far, the gas is much cooler. So here most of the variations in the light curves, they are explained by the relativistic shocks that are propagating down the jet. So they explain most of the variability from the radio through optical observations. On other models which can explain the variability involves the turbulence, instabilities, or magnetic inhomogeneities in the jets. So here also you can see that there is frequency stratification behind the shock. So first the higher energy electrons are available for the synchrotron emission, and then lower energies as we move away from the shock. Blazars are variable on all accessible time scales from minutes to months to years, and when we need long-term observations, so these small telescopes play important roles. So the work that I will show, I have used all these telescopes from Aries 1 meter, 1.3 meter, and few telescopes from China, Japan, Spain, Bulgaria, and Serbia, Georgia. So here you can see that there are various size of telescopes which are used for these studies, like 1 meter, 1.3, and the smallest one is like 40 centimeter. So I will talk about few of the results that we have done for the blazars. So here you can see the first project is the optical variability of blazars on IDB time scales. IDB means which the observations are done on an in a particular night on minutes like time scale. So we just wanted to see what are whether the fluctuations are there or the variations are there on hours like time scale. So we observed this source. This is a blazar, and it was in a high state. High state means the uh, flux was increasing in that particular time as compared to the normal one. So here you can see that this top one is the differential light curve of the blazar, and this is the star 1 minus star 2. So we try to find out the variability time scale and the size of the emitting region for this source, but we did not find out. The second one is the constraining the duty cycle of different classes of blazars. So we performed optical monitoring of about 2 dozen of different classes of blazars and BB array bands, and these results are based on these papers. So here you can see that we constrain the duty cycles of different classes of blazars. So duty cycle means number of observations in which a source was variable out of the number of in total number of nights in which we observed them. So here you can see that LSPs are like 51% variable, 51%, and the duty cycle of HSPs are like very less, 8%. And this less detection of IDV of HSPs is in agreement with the conclusions of the previous studies, which says that these sources are intrinsically less variable in optical bands, and the differences can be explained because of the differences in their spectral energy distribution. So here you can see that the peak of the first hump of these sources, they lie above the optical bands, and hence these sources, highest energy electrons are available for the synchrotron emission in optical bands, and hence these sources are more variable, and hence they have higher duty cycles as compared to the sources which have SCD peak in the X-ray bands. So they are less variable in optical bands. Now, we also observed many blazars for the short-term variability studies, and like months like time scales or years like time scales. And here we just try to find out the possible models which can explain the flux variations and the color variations. So here we studied the color variations. Like you can see that we studied the color versus magnitude, and if there is a positive correlation between the color and magnitude, so the source shows bluer and brighter trend, and when there is a negative correlation, so then there is a redder and brighter trend. So all these results, they can be explained in the framework of the existing models, where the like for the bluer and brighter trend, we have Shocking jet model, where higher frequencies are first emitted and then lower frequencies as we move far from the shock front, and hence the sources show bluer and brighter trend. So such type of projects are very important, and one can study the spectral slope distribution or in optical bands. So here what we did, that we took a set of BVRI using various telescopes for a sample of for a large sample of LSPs and ISPs and HSPs, and we try to find out how the spectral slopes varies with respect to frequency. So these spectral slope studies are very important, as they tell us what are the possible mechanism. Like for LSPs, alpha was greater than 1, and it accumulates approximately around 1.5. And these type of observations shows that there is synchrotron self-compton loss dominated synchrotron emission model. And for HSPs, so spectral slopes, they ranges between 0.5 to 1.8, which indicates that the optical emission, they are contaminated by other components such as thermal contribution or other non-thermal contaminants, because these sources are very nearby. So there are host galaxy contributions also. So one has to subtract the host galaxy contributions in order to study the spectral slopes. Now I will talk about the correlated variability studies of blazars. So cross correlation analysis of the multi-wavelength data is very important in order to find out the possible time delays. So what happens when there is a flaring in the optical band? It could happen that there is flaring in the other bands, in the high energy bands also, like gamma rays or X-rays. So using cross correlation studies, one can find out whether one can confront the framework of the existing models like external Compton or the synchrotron self-Compton. So in this particular observation, so this data has been taken from Aries in 2009 to 10 and from other telescopes also, and we find out a flare is happening here. So this flux suddenly rises. So we try to find out the cross correlation with respect to the gamma ray band, and we find out that the gamma ray and optical are correlated with a time lag of 4 days. So which it supports the existing external Compton model, which says that the synchrotron electrons, they first emit the synchrotron photons, and then the same electrons, they upscatter the external photons up to the gamma ray energies, which lead to such type of flares in the gamma ray band. We also extracted the X-ray band from the MAXI satellite, but we find out that there is no flaring even, and hence it can be explained that it might come from the some lower energy electrons, which are not varying much as compared to the optical and the gamma ray bands. So when such type of monitoring is required, so these are very good projects one can do with the small telescopes, because long-term monitoring is required for such observations. Another example of the correlation studies of B.L. Lekerte, and here I performed a cross correlation of the optical and the radio bands for this source. So this source was in a very high state, means the flux was increasing in that particular time. So we cross correlate with the radio data, and it was a big campaign in 2010 to 2013. So we cross correlate the radio and the optical data, and we found a lag of around 250 days between the optical and the radio frequencies, which can be translated into the distance of approximately 12 parsec from the central engine. So means here you can see this is the model which can explain these observations. So here this is a jet which is inhomogeneous, means different parts of the jet, the different parts of the jet, they emit different frequencies. Closer to the jet, there are optical frequencies, and as we move along the jet, so the radio frequencies are emitted, and hence there is a time lag of approximately 250 days. So the distance between the emitting zones of optical and the radios are approximately 12 parsec. Now I will talk about the optical flux and polarization variability of blazars. So blazars are characterized by high degree of optical flux and polarization variability owing to the synchrotron emission, and it is found that there are sometimes positive correlation between flux and polarization, and there are sometimes negative correlation between them. And this is a very important work where people have these Blino et al. Has done, that there are polarization angle swings also along with the flux variations. So using the aim pole at Aries, we are observing a sample of blazars, and we are trying to find out whether there are polarization angle swings along with the flaring activities in the blazars. So such type of projects are also very important to do with the polarimeters. And the next project is the optical variability of newly discovered blazars from Roma BZ CAT catalog. So this is our ongoing project which we are doing using Aries telescope. So the Roma BZ CAT is a multi-frequency catalog of newly discovered blazars, and it contains approximately more than 3,500 sources. So their optical variability properties are not yet studied, and approximately 227 sources are such that they are not known whether they belong to blazar class, but they have few properties blazar-like properties. So one can study such type of sources using the small telescopes, and one can characterize the optical variability properties of such type of sources. So here I'm just showing a work which is done using the Aries data. So it is done by Kalida et al. 21, and here you can see they have studied they just constraints of few other parameters using the variability properties of these newly discovered Broma BZ cat catalog blazars. So the future perspective with these small telescopes, so yeah, so I will just talk about this work also. So in big multi wavelength campaigns, small telescopes play an important role in the sense when the source goes in flaring state or in very low state. So what happens is spectral energy distribution in order to constrain the jet parameters. So what are the jet parameters which lead to such type of flaring activities? So in order to constrain the spectral energy distribution, one needs the simultaneous observations on optical and from the radio to the gamma ray bands. So this is the work done by Hayashida et al. 2015 APJ, and we contributed in this work. And this optical observations were taken from many telescopes around the globe, and the Aries also contributed in it. So I just want to emphasize that these small telescopes, they are very useful in coordinating the multi-wavelength observations and in coordinating the optical campaigns around the globe. And so these are the projects which I already mentioned, that in these newly discovered Roma BZ catalogs can be observed using small telescopes. One can do the flux variations, polarization studies, and these type of small telescopes, they can participate in the multi-wavelength projects also, like cross correlation studies or in the construction of the spectral energy distribution. So there is a very important role of these small telescopes in blazar studies. So I will stop here. Thank you.
Thank you so much, Dr. Hartima, for a nice talk. Now it's time for a few questions.
Oh, can I ask the question?
Yes, Raghu Krishna, you can ask.
Okay. Thank you for this wonderful talk, ma'am. I have two short questions.
Yes.
First is, what does the infrared and the near infrared and mid infrared observations of blazars tell us? Is it are they from synchrotron emissions or are they thermal emissions?
Can you repeat the question? I am not able to hear you properly.
What does the mid infrared and near infrared data of blazars tell us? Are they from synchrotron or thermal?
Are they consistent with?
From non-thermal or thermal?
Yeah, the infrared observation. So most of the emission, they are coming from they are the non-thermal emission. Most of the emission is across the electromagnetic spectrum is only the accretion disk, like optical and some. So if we are able to see the accretion disk, like in a subset of blazar, like flat spectrum radio quasars, we are able to see the accretion disk. So sometimes we are able to see the accretion disk component, which is thermal, but most of the time we are able to see the non-thermal part, which is coming from the jet.
But if we observe other than radio, if we observe the blazars in infrared or optical band, are we seeing them? Are we seeing the host galaxy, or are we seeing the jet?
Yeah, mostly we are seeing the whole jet part, but sometimes we are able to see the host galaxy if it is very nearby blazar. But these are very far. Most of the sources like quasars, they are very far off. We are not able to see the host contribution. For few sources which are very nearby, so we can just see the host galaxy contribution in the optical bands.
Okay, my second question is are there any blazars for which there are no gamma ray or X-ray observations, and no, even UV, gamma ray, and X-ray are absent? Is it possible to have such blazars?
No, it is not possible. Most of the times they are correlated variations are there.
For the
Most of the time, not always.
For the high redshift ones?
Yes, for the high redshift one also.
Okay.
Yes, Professor Chakravarti, you can ask your question. Hello.
Hello. Hello.
Yeah, Professor
Yes.
Sandeep
I'm
Chakrabarty,
sorry.
you can ask your
Yes.
question.
So the question is that since in a small telescope the field of view is very big. Big means in our case, let us say 0.13, I think 13 half minute or something. So if you consider a quasar where there will be some matter in front of the quasar also, so is it not possible that the small telescopes will add contribution from the front matter also more than larger telescopes whose resolutions are high and they can concentrate on a specific region of the quasar or something. I mean, small telescopes being seeing a larger field of view, so I thought that there could be more contamination from the front matter of the matter between us and the quasars. Is that a problem, or has it been felt that this is a problem?
Yeah, we have also used the small telescopes, but we have never faced such type of problem, because most of the time the means calibrating stars and the are in the same means field of view, and they are close by. So this line of sight problem which I was saying, I have never seen it. Maybe most of the sources that we have observed, they don't have much line of
Such
sight.
matter.
Yes.
But there could be warm absorbers or some, I mean, like in front, and the effects will be much larger if a small telescope is used. That's what my feeling is. But maybe if it is
Um,
not there, I will be will be very happy because if small telescopes are not a problem, then we will be very happy to join such, getting the spectra of the quasars and the
yeah, sure, sure. Actually,
and
most of the time we used to observe lasers. Most of these works are done when the source is in very high state, so they can be easily catched by the small telescopes.
okay, sure, thanks.
Yeah,
So if there are no more questions, then let's thanks the speaker again.
thank you very
Our,
much.
our next speaker is Dr. Ashish Raj. Has done his PhD in 2012 from Physical Research Laboratory. He also worked as a postdoctoral fellow in TRL between November 2012 to March 2014. He joined Korea Astronomy and Space Science Institute, Kasi, South Korea for his second postdoc in April 2014 and was there till March 16. Then he moved to IIA Bangalore for his third postdoc in July 2016 and was uh, there till June 2019. Before joining ICSP in August 2022, he worked as a research associate in University of Delhi between October 2019 to March 2022. He is a life member of Astronomical Society of India and a former member of Korean Astronomical Society. His main area of research is ancient sources. So I welcome to Dr. Ashish Raj. Yeah.
Yeah. Thank you, Devin. Today I'll be talking about one of the NOAA which I studied during my PhD in 2013 sometime. And this object was finally suggested by astronomers as a recurrent nova, and there was a paper in last month by Schiffer et al. That this is a recurrent nova. So before presenting my talk, I'll be giving a brief introduction about the novae and their classification, and then the results which we have obtained for this particular nova, and then we will summarize the results. So the classical novae are actually binary system where one star is a white dwarf star, which is a primary star. It's a degenerate core of matter, and it is accreting, and the other one is a secondary star, can be a main sequence or giant star. So you can see in the picture the secondary star is actually losing its material through its inner Lagrangian point, and it is forming an accretion disk around the white dwarf. And when the density reaches a certain limit, the thermonuclear runaway reaction starts at the surface of the white dwarf, and we see a sudden brightening in the system. So nova is actually a Latin word that means a new star in the sky. So I got a small animation from NASA, which can easily depicts what exactly the nova system is. So I'll just, you can see the picture here. Center is a white dwarf, secondary star here, and it's accreting matter, and now the outburst. So you can see the material is actually being ejected in the interstellar medium, and you can see the foreground and background stars, and the nova itself looks like a new star in the sky. Okay, so there are different phases in the outburst, after the outburst. So initial phase is fireball, where it behaves like a pseudo photosphere of a A2F spectral type star, having temperature around 6,000 to 10,000 Kelvin. And after some time, when nova, the ejecta expands, it starts showing deviation from the black body, and that is called the optically thin expansion phase. And most of the time it fits with the power law. And at some case, around 25 to 30%, we can also see molecule formation as well as dust formation in these nova ejecta. So that can be attributed as a sudden dip, which we can see in the optical light curve, that means V-band light curve. So these are the typical nova light curve. You can see initially it's a pre-nova phase, where you will not be able to detect the nova, and suddenly it rises, and there is a pre-maximum halt, and then it starts declining. After reaching a maximum, it starts declining, and then around 3.5 to 6 magnitude, it shows some transitions, and then it finally goes to its quiescence phase or post-nova phase. So there are different light curve classifications for these novae. So that was given by Stope. They took around 93 nova light curves, and they tried to classify it on the basis of the shape of the light curves. And they classified it in 7 different categories: F, C, J, T, O, S, and D class. So this KT Iridani is actually a P class nova, where we have seen plateau in the light curve. So there are another classification, which is spectral classification, because most of the lines which we generally see in the system, they generally have hydrogen and helium, because the outermost layer of the star is generally consists of all these elements. So we have to look for other lines in the star in the spectra to classify it. So so there are 3 different classifications given by Williams et al. And one is Fe2 class, where we see P Cygni profiles, and they show most of the lines from iron to, and some low ionization lines like sodium and magnesium, and they generally come from CO type of white dwarf. And then the second one is HEN class, that generally comes from oxygen and magnesium kind of white dwarf, and they generally have fast evolution, high expansion velocities, and show mostly helium and nitrogen lines. And there is a third one which shows both the classes in a single evolution, in a single outburst. And initially you will see a P Cygni profile, and then the ejecta velocity is low, and suddenly before going to the nebular phase, it starts showing the HEN class of nova behavior. So we call it as a hybrid nova. So this is the figure we can see here. The left one, topmost, is Fe2 class nova, where most of the lines are from iron, and the right one is HEN class nova. Mostly helium and nitrogen lines are seen, and then hybrid nova, where initially the lines are narrow and iron lines are also present, and then they all are gone, and suddenly the line widths are also getting broader. So this is hybrid class. So KT Iridani came in outburst in 2009, November 25, and it was discovered by Itagaki at 8.1 magnitude. But some of the archival plates taken by other astronomers, when they looked into that, they find that, okay, this nova was also in outburst around after around November 10. So it was out. It was in the outburst before 15 days of its actual discovery. So you can see on the table itself, it was around 14.5. So around 14th November, it was at the peak. And here on the left side, you can see the light curve. That is the time evolution brightness of the change in the brightness of the nova with respect to time. So here you can see different plateaus are seen. First plateau, second plateau, and this is the quiescence. So these are the spectra which these all are taken from 1.2 meter telescope at Mount Abu. So you can see most of the lines are from helium and nitrogen, oxygen, and Bragg series lines are seen in HB spectra. So we also noticed that there was a bipolar flow in the lines. So that means we can see a bipolar morphology for this ejecta material, and we have also tried to fit the Gaussians for to look for the velocity of the components. So the central component is actually is coming from the equatorial region, and the left and right wings are coming from the polar regions. So that means the ejecta is actually moving more freely in the polar direction as compared to the equatorial region. And Ribeiro also tried to use shape and try to look for the inclination of the system, and he got around 58 degrees inclination for this particular nova system. One more thing which we started to look for this nova was the evolution of its continuum, how it evolves with time. So we know that the black body generally fits for alpha equals to 4 at longer wavelengths. So initially it was around 3.34 on 20th November, and slowly it starts decreasing, and it was reached up to 2.67 at a later stage. So that was the peak, and that was the peculiar thing which actually was not done for any nova, because this SED is covering around UBBRI and JHK bands, and we got the alpha values were around 2.67. So we also look for any possibility of its being a recurrent nova of RS Ophiuchi type. So we try to see the bracket gamma line profile evolution with time. So since we know that RS Ophiuchi has a giant star as a secondary, so whenever ejecta expand, it's interact with the secondary. So we should see a change in the line profile. That means we should see the change in the line width of the lines of bracket lines and bracket gamma and Paschen beta lines in the infrared. But we didn't see anything. So we can say that this nova is actually recurrent nova, but the secondary is not a giant star, but can be a evolved star. So another point which was seen in the nova was the 35-second oscillations, X-ray oscillations in the supersoft X-ray emission phase that was reported by Ness et al. And Nelson et al. So recent work by Schaeffer in this on this nova, they used test data and or other available data from SMARTS, and they try to find out different physical properties of this system, which was listed in the table. So they also predicted that the recurrence time for this nova is around 40 to 50 years. And this is the Lomoto plot for calculation of the recurrence time with respect to the accretion rate and mass of the accreted material. So the blue circle clearly indicates that the nova lies in this particular region, and these lines are actually the time after which the nova should come in the outburst, or the TNR should start at the white dwarf surface. So here you can see this clearly indicates that this value is around something like 5 to 50 years, in between 5 to 50 years, and they also tabulated this result in their table. So you can see from the table, they just try to look for the archival data for this object, and they predicted that the accretion rate is around 10 to the power minus 7 solar mass per year, and the NOAA should come between 5 to 50 years. But they also put some criteria for recognizing this NOAA as a recurrent one. So the amplitude of the NOAA was around 9.2, so which was actually in the range, and the orbital period they estimated was around 2.6 days from these test data, and the colors and other things also they estimated around 0.1 and 0.07. So most of the things, if you look at the table, most of the things are actually lying, actually matching with the recurrent NOAA. So they finally concluded that this is actually a recurrent NOAA. And this is the picture of the KT Dani system they make using the softwares, and there they have clearly mentioned about the temperature of the secondary star, the accretion disk, and the radius of the star. And this is the summary. So the infrared spectra actually indicate that this is actually a chain class nova, and from the there is a bipolar ejection. So we also see the possibility for this Kriti Iridani as a recurrent nova, and we found that most of the properties are actually matching. We are matching with the another galactic recurrent nova, V745 ISCO.
Okay. Thank you so much, Dr. Asu, for nice talk. So now it's time for the questions.
Yeah, light चला गया. What happened?
Hello. So thank you so much, Dr. Ashish Raj, for nice talk. Now it's time for a few questions.
Yeah.
So if no more questions, then all the participants can download your certificates. The link is given in the chat box, so you can download your certificate after giving your feedback. So please download your certificates from there.
So our next speaker is Dr. Devendra Bist. He has done his PhD from Department of Physics, Kumai University, Nainital, India. He was a postdoctoral fellow at Physical Research Laboratory, Ahmedabad, India from 4th May 2016 to 3rd November 2017. He joined the Department of Astronomy, University of Science and Technology of China from January 2018 to December 2020. He was a PDF in IIA, Bangalore, from June 1st, 2022, August. And since 25 August 2022, he has been associated with ICSP Kolkata as Scientist C. He is a life member of Astronomical Society of India and a junior member of India's International Astronomical Union. His main research interests are multivariate studies and variability on open star clusters and the study of transiting exoplanets. Okay.
Yeah, thank you so much, Dr. Asisras, for the introduction. Myself, Developist, and today I am going to deliver a talk on variability of stars in open clusters. And can you see my screen? Yeah. Okay. So, stars are born from huge cloud of molecular pairs. Since this molecular cloud composed of hundreds of solar masses of material, then stars generally form in groups or clusters. So star clusters are formed at the same time, and they all are situated at the same distance. They form from the same material, and only difference is their masses. So star clusters can be classified into two main categories: globular star clusters and open star clusters. So as you can see, globular clusters are spherical in shape and very dense, and a huge number of stars are there. They are population type second object. And in case of open clusters, they contain few tens to thousand number of stars, and they are very young than globular cluster. So open clusters contains few tens to thousand number of stars and a very young population type one star. That means higher in metallicity, and they may still be surrounded by nebula from which they form, and they are located on the spiral arm and galactic disk of the Milky Way galaxy. That's why they are also called galactic clusters as well. And in the background, you can see the image of Pleiades, and you can see through the naked eye if the sky is very clear. Then few stars you can see from the Pleiades clusters. So here you can see how it looks like. Here in this picture, you can see two different clusters. One is Major 35 and the other one is NGC 2158. So this one is very young, and this 2158 is very old. So you can see on the based on their ages, so their distribution is also looking differently. So we also studied this object NGC 2158 last year using the data. Now, variable stars, actually the brightness of a star as seen from the Earth changes with time, so that is called variable star. So here you can see the image of a star, the same image in two different pictures. So you can see in the left one, the star is looking very bright, and but the right one, the same star is looking dim. So this is because of the variability in brightness. So variable stars are basically two types: intrinsic and extrinsic variables. And the stars has its own characteristic properties to swells and shrink itself. And if the luminosity is actually changing, so that's why we can classify intrinsic variable stars in pulsating stars and eruptive catalysmic stars, which have categorized in many supernova, nova, recurrent nova. And last speakers discussed a lot about the variability, and the Dr. Ashish Raj also discussed about nova, recurrent nova. And in extinction variables, if someone is blocking the star's flight, like the companion star, so based on that, we can write an eclipse binary and the rotating variables. Hurstman-Russell diagram is mostly useful and powerful diagram in astronomical research. And when we plot HR diagram for open clusters, then most of the stars lie along a diagonal line, which is known as the mean sequence. And other major groups, also you can see here giants, supergiants, white dwarfs also here. And on the right side, you can see the region of the variable stars, which kind of variable stars generally we can see on the color magnitude diagram of stars. So here, the type of variable stars, this region is delta Scuti type variable stars, where delta Scuti type variable stars generally found. They are very short period, and they sometimes they generally called as dwarf Chaffetz. So beta Chaffetz variables actually a star that pulsates radially, varying in both diameter and temperature and producing changes in brightness. They are called Chaffetz variables. And RR Lyrae variables are the periodic variable stars and generally found in the globular clusters. And they are used as standard candles to measure galactic or extragalactic distances. And here you can see also the Mira variable stars, which are very high periodic variables, mean around more than 100 days. Now, come to this study, we have taken sensory photometric observations for these four clusters, B69, King 17, Berkeley 20, and uh, from using 1 meter Sampunal telescope at Aries. And here is the identification charts, and the green one are indicating the variable stars which we detected in those regions. And this image is simply vector point diagram, which are showing the distribution of all stars, and the middle one are the distribution of cluster stars. This is color magnitude diagram, and this is proper motion distribution, and this is the field star distribution. And we have shown the variable stars here with green dots. So using this vector point diagram, we have also estimated membership probability, because open clusters generally found in the more populated area in the galactic plane, where field region stars generally contaminated, especially towards the center end. So that's why it's very important to remove all the field stars from the cluster sequence in order to find the precise measurements of all the parameters and to search the true variable stars. So here we have fitted theoretical isochrones given by Marigo et al. With metallicity 0.008 for B69 and King 7, and for we used solar metallicity isochrone for King 5, and we have estimated distance, age, and other parameters from here. As you can see, we have estimated the astrophysical parameters for these clusters. And now they come to the point, the variability for B69, a total of 4 stars were found to be variable. This is light curves of those stars. And the light curve of these variables, along with the differential light curve, is and comparison stars are also shown in this figure. All stars are showing some irregular behavior. So no periodicity was seen in V1, V2, and V3, but we found V4 is showing periodic variable. And this is power spectra, and power spectra for V4 star, and where you can see this is the highest peak, which corresponds to 0.225 days or 5.4 hour. So we have folded the data using an arbitrary ephemeris and period of 0.225 days. And on the right side, you can see the folded light curve with the best fitted sine curve. And based on the position of this star on the vector point diagram and color magnitude diagram, so we concluded that this is spectral type H0 stars, and maybe this may be field region stars. On the basis of VPT. And for King 7, we also checked for the variability for those stars, and we found V1, V2, V5, V6 are showing periodic variable with period 0.13 to 0.21 days, and all are early A-type star. So their periods, amplitude of variability, and spectral type indicates that all are delta Scuti type variable stars. And also the right side is the folded light curve with best fitted sine curve for these variable stars. And for King 5, we found only one star. P5 is showing some periodic variable, and the period is around 0.15 days, and this is also A-type stars. We can conclude that this is also delta Scuti type variable stars. And for BA20, we found V1 and V3 are periodic variables with a period of 0.19 and 0.219 days. And we found that these two stars are G-type variable stars, so maybe they are W Huma type variable stars. So here is the table for all the variable stars with their brightness, the color, and the period, and the probable spectral class. And this is color composite diagram. And here we fitted theoretical isochrone of different different ages, 0.79, 1.58, and 5.01 gigayear based on the age of our clusters. And this strip, you can see this is delta Scuti instability strip. And we found 5 stars from King 7, 1 star from B69, and 1 star from King 5 is near to this delta Scuti instability strip. So maybe a few of them maybe are delta Scuti variable stars. And we have also checked the mass segregation story. Mass segregation is the when the two stars are come closer, they exchange their energy and momentum. Energy can be exchanged in either direction. So there is a statistical tendency to equalize kinetic energy during an encounter. This statistical phenomena is known as equipartition of energy, and this encounter continues until the system becomes relaxed. So in mass segregation, the massive stars give kinetic energy to low mass star, and low mass stars try to move out to the system, which leads to the core halo structure may be found there. So to check mass segregation in those clusters, we first distributed these cluster stars into three different mass ranges, as you can see here, and then we plotted cumulative radial density profile. And we have also checked this using some statistical test, Kolmogorov syndrome test, to see the statistical significance. And we found around 99 and 99% for King 7 and 95% for King 5. These two clusters are influenced by the mass segregation effect. But in case of B69, we found the confidence level is just 30%. So this cluster is not influenced by the mass segregation. So as we can see, we didn't search two and many variable stars in those clusters. So here we have 0.61 meter optical telescope. So we are planning to take time series observations for those clusters and many more unstudied clusters from 24-inch optical telescope here to search the true number of variable stars. And one of our main aim is study of distribution of open clusters in the 60 phase space using ground-based observations along with the Gaia DR3. And we are also planning to use our observing facility to observe transit events. The data will then be combined with already available data to elongate the time baseline for transiting exoplanets. Thus, transit timing variations can be studied from here. So, thank you so much.
Yeah, so thank you, Devendra. If you have any question, yeah, Devesh.
Devendra, what is your main criteria to, classify the variable stars? How do you classify? How do you know that it is a delta Scuti or some other? Yeah, like some of them could be binary stars, which are, already, which are so many. There are so many possibilities of having binary stars in an open cluster. So how do we know that it is a delta Scuti or some other kind of star? How do you classify? Hello, am I audible?
Yeah, yes, yes. Actually, on the based on the Pleiadian analysis and their position on vector point diagram and color magnitude diagram, we concluded that these stars may be delta Scuti variable stars. Actually, we are not strongly saying that they all are delta Scuti. We have just conclude that they are very near to delta Scuti instability strip region. So maybe few of them may be delta Scuti variable stars. So for to detect very carefully, very accurately, we need time series observations. Actually, these all observations are only 1 night or 2 night data. So that's why we are planning to take time series observations for all these clusters to search the accurate number of variable stars.
But when we say that one of the stars in the first cluster that you showed, it was not a cluster member, right? You said it is a field star.
Yeah, actually, we estimated membership probability of that star and their position on the vector point diagram. We found that this cluster is somehow coming out of this circle which we have we generally use for the selection of cluster star. So that's why that's why maybe that is field division star.
Yeah, I understand that.
Yeah.
So when we say that it could be a field star, so in that case, I think we cannot use the instability strip because it is only for the color magnitude diagram of a cluster. It will not be valid for the field stars. Is it so? Because field star can be at any distance. It may not the field, right?
Yes, yes, it may be possible, but we didn't conclude that that star is the delta scuti variable stars. Actually,
Okay.
we concluded that that particular star may be Hildebrand star. So we didn't include that in our conclusion.
Okay. Okay. So what is the what type of variable star is that? Means the rough uh,
Roughly,
calculation.
we found some delta scuti because the data was just 1 night or 2 nights, so we can say that they are short period variable stars. So maybe delta scuti variable.
Yeah, maybe we can also look at the
Yes,
shape of
yes,
the
yes,
color shape of the light curve along with the period.
yes, yes,
I
yes,
know that you took into consideration the period, but shape of the light curve is also very important in
yes, yes,
such
yes,
cases. Yeah.
yes, yes, yes. Yes, thank you.
Thank you, Devendra.
Oh, oh.
Mute yourself. Okay, so Sandeep also have one question. Professor Sandeep. Devendra,
Yeah.
there is one more question.
Yeah, hello.
Professor Sandeep, you can ask your question.
Yeah, Devendra.
Yeah, yes.
Yeah, the question I am asking is that what is the possibility that these some of the variabilities are due to the solar kind of flare like magnetic recombination or flare like events. So are they common in the objects in the globular cluster, or they are uncommon? Do they have magnetic fields in these stars in the globular clusters, which are supposed to have not much metal, but is there any rule on that? Do you know?
So I don't think that actually. Uh,
No, no, like if you have a
yes,
flare, if the stars have flares, it can
yes,
also, of course, or outflows, sudden outflow, sudden mass
yes.
ejection of, coronal mass ejection or something. Is there any way, do they affect the variability?
Yeah, maybe they will definitely they can affect the type of variability. Yes. So for that we need to take time series observations and to draw light curve for many night data actually. So that's why we can conclude that exactly what kind of variable star that is, and is there any such kind of mechanism who is affecting the type of variable stars. So in case
I
of
think if it
yeah.
is due to the flare, then it will not be periodic. It may have sudden outburst.
Yes,
If
sudden
it is
outburst.
a sudden outburst, so it will not repeat on a regular interval. So the period
Yeah,
will
they
be
will be
very
like fast rise, slow decay, something like what we
yeah.
see in
So
the
the
case of.
light curve will be different. Light curve will not be periodic like these light curves.
Okay.
That's why we need to have more data to so that it can be repetitive and we can be confirmed that
Yeah.
they are
Yes,
No,
yes,
my
yes,
question was that whether these set of objects fundamentally do they have sun-like behavior in terms of as long as far as the magnetic field goes. I mean, these objects in the globular cluster, do they have strong magnetic field? That is my question. First question, and then this flare part comes in.
okay.
they should have like they have the same some of them have the same you know sun-like spectral classes, so they may have magnetic variables. There is a possibility, but we should have the observation and the apparatus to detect them. They should have those kind of variables.
Okay. Now sometimes their how their progenitors, sorry, their history and the environment where they were born, whether they were suppose the first generation stars, maybe the magnetic field was not strong enough. So suppose, so in which case the magnetic fields not necessarily be as strong as what we see in the case of the second generation stars. So is there any way to distinguish between the first generation and second generation in terms of the strength of the magnetic field or flares? So these I am asking a little more fundamental questions, whether these can be which can be sorted out by this kind of observations or not.
in open clusters, we can, if we study like older open clusters and younger open cluster, and then we make a comparison, then your question can be answered. Maybe we have to see,
Okay.
look at the data of, different
That means
ages of open
you
clusters.
need to take different type of open clusters with different age actually.
Okay. So, is there any Ashish? Is there any concluding? If somebody is concluding the
Yeah, yeah.
conference,
So,
are you
yeah,
do
yeah,
that?
yeah. So, Devendra is
Okay.
going to conclude the session. So, I would like to invite Devendra to conclude the session.
Yes. Thank you. So on the behalf of the Indian Center for Space Physics, we would like to thank all speakers for their valuable presentations at our symposium on the role of smart telescopes in exciting areas of observational astronomy. We want to thank everyone who attended the symposium and the organizers for their hard work putting together a fantastic event. We hope that everyone who attended found the symposium informative and beneficial. We also encourage everyone to continue exploring the exciting science field and share their findings with the world. We look forward to seeing you everyone at the next symposium of ICSP. Please give your valuable feedback and download your certificates from the given link. Link is given into the chat box. So thank you so much.
Thank you very much, Devendra. It was a great meeting. I am very much happy and encouraged.
Thank you so much, sir.
Yes. Thank you,
Thank you, sir.
Ashish.
Thank you. Thank you, sir. Thank you.
Thanks. It was a great meeting. Very nice.
Yes,
Thank
thank
you,
you.
sir.
Thank
Thank
you.
you. Thank you very much.
Thank you,
Thank
everyone.
you, Guru. Thank you, sir. Thank you very much.